From. Right now, as you settle in, there are roughly 250,000 lightning strikes happening across the Earth every single day, each one a plasma channel hotter than the surface of the sun, lasting less than a millisecond. You have never once stopped to find that strange. From. And the screen you were looking at earlier tonight, its light reached your eyes not as a smooth river of energy, but as a procession of individual packets, each one a discrete bundle delivered one at a time, arriving so fast the whole thing feels continuous. From. The universe at its smallest scale operates by rules so alien, so stubbornly resistant to common sense, that the greatest minds of the 20th century spent decades arguing about them in furious letters in crowded conference rooms. Some never made peace with what the math was telling them. From. Tonight we are going to walk through all of it, slowly, no pressure. If sleep finds you somewhere in the middle, that is exactly as it should be. What we are really talking about tonight is a question that has no clean answer and never has. From. Not a question about particles or waves or equations, but a deeper one underneath all of that. The question of what reality actually is when nobody is looking at it. Quantum mechanics is the most precisely tested scientific theory in human history. It has never once been wrong in a way that mattered. From. And yet after more than a century, the physicists who use it every day still cannot agree on what it means. That tension between a theory that works perfectly and a theory nobody fully understands is what we are going to live inside tonight. Slowly, gently, one idea at a time. From. And the reason to care about this right now tonight is not abstract. The device you are holding or that is sitting on your nightstand is a quantum mechanical object in the most literal sense. The chips inside it were designed using equations that describe probability clouds, not definite positions. From. The light from its screen was produced by electrons jumping between quantum energy levels. The memory storing everything you have ever photographed or written relies on electrons tunneling through barriers they have no classical right to cross. Quantum mechanics is not a theory about things too small to matter. From. It is the foundation of the physical world, including the parts of it you can touch. So let us start where any honest account of quantum physics has to start. Not with an experiment, not with an equation, but with a mood. The mood was confidence. It was the 1890s, and physics felt nearly finished. From. Isaac Newton had given the world a mechanical framework more than 200 years earlier. He had described how objects move, how gravity pulls, how forces act. His laws worked for planets and pendulums and cannonballs, and they worked with a precision that felt like proof of something absolute. From. Then James Clerk Maxwell, a Scottish physicist working in the 1860s, had produced 4 elegant equations that unified electricity and magnetism into a single coherent theory and predicted the existence of electromagnetic waves traveling at the speed of light. From. In doing so, he accidentally explained what light itself was. That was not a small thing. That was one of the great unifications in the history of thought. By the 1890s, thermodynamics was well established. The periodic table was filling in. From. The kinetic theory of gases explained heat as the motion of molecules. There was a widely circulated sentiment, sometimes attributed to Lord Kelvin and sometimes to others, that physics was essentially complete, that what remained was simply to measure things more precisely. From. To add decimal places to constants that were already known. The architecture of nature, it seemed, had been fully drawn. All that was left was finishing work. This feeling was not foolish. It was a reasonable conclusion from the evidence available, and it was spectacularly wrong. The cracks were already there. From. Small ones, easy to dismiss, but real. A handful of experiments giving results that the existing framework could not explain, and one of them involved something almost embarrassingly mundane. The way hot objects glow. You have watched this your whole life without thinking about it. From. A piece of metal in a fire starts dull red, then brightens toward orange, then yellow, then a blinding white as it gets hotter. The color shifts with temperature reliably, always in the same direction. Physicists had measured this relationship carefully. From. They had produced precise experimental curves showing exactly how much energy a hot object radiates at each frequency of light, and then they had applied Maxwell's equations and classical thermodynamics to predict what those curves should look like. The prediction was a catastrophe. From. The classical calculation, worked out carefully by Lord Rayleigh and James Jeans, said that a hot object should radiate more and more energy as you move toward higher frequencies, toward violet light, toward ultraviolet, toward X-rays, and beyond. The predicted energy just kept climbing. It went to infinity. From any warm object, according to classical physics, should have been radiating infinite energy at high frequencies. Your coffee mug should have been killing you with radiation. Everything warm should have been a death ray. The name given to this failure was the ultraviolet catastrophe, and it was not a small discrepancy. It was not off by a few percent. The theory predicted infinity where the measurements showed a gentle curve that rose, peaked, and then fell back down. Something was not merely wrong, something was fundamentally broken. The man who repaired it reluctantly, almost accidentally, was a German physicist named Max Planck. He was born in 1858 in Kiel. He was orderly, methodical, deeply conservative in his thinking. His professor at Munich had reportedly advised him against a career in physics, telling him the important discoveries had already been made. Planck later said he had not been looking for new territory. He just wanted to understand the existing foundations more deeply, which makes what he did in 1900 all the more striking. Planck was trying to find a mathematical formula that would match the experimental data for black body radiation. He wanted an equation that reproduced that gentle, well-measured curve. And he found one. It worked perfectly. But to make it work, he had to introduce an assumption that he himself found deeply uncomfortable. He had to assume that energy was not continuous. That matter could only absorb or release energy in discrete chunks, fixed indivisible amounts, each one proportional to the frequency of the light involved. He called these chunks quanta, from the Latin for how much. And the proportionality constant connecting frequency to energy was a new number, tiny almost beyond imagining, that we now call Planck's constant. Think about what this meant. In classical physics, energy is smooth. You can have any amount you like. It flows like water. What Planck was proposing was that energy is actually granular, like sand. From a distance it looks continuous, but up close it comes in individual grains you cannot subdivide. You can have 1 grain or 2 grains or 1,000,000 grains, but never 1.5. Planck did not believe this was literally true. He was explicit about that. He described the quantum hypothesis as an act of desperation. He had tried everything within classical physics and nothing worked. The quantum was a last resort, a mathematical device to make the formula fit the data. He assumed someone would eventually find the proper classical explanation underneath. That explanation never came. And the number itself, Planck's constant, is so vanishingly small that in the everyday world, the graininess of energy is completely invisible. The quanta are too tiny to notice at the scale of cups and tables and human hands. But at the scale of atoms, that graininess matters completely. It changes everything. And on the 14th of December 1900, Planck presented his quantum hypothesis to the German Physical Society in Berlin. Physics had just changed forever, and almost no one in the room understood that yet. 5 years passed. Then a 26-year-old patent clerk in Bern, Switzerland, picked up the idea and did something with it that Planck had not been willing to do. He took it seriously. Albert Einstein in 1905 was not yet the Einstein of legend, no wild white hair, no global fame. He had failed to secure an academic position after finishing his doctorate and was working as a third-class technical expert at the Swiss Federal Patent Office, reviewing applications during the day and doing physics in what was left of his time. That year, 1905, he published 4 papers in a single burst. Each one would have been enough to define a career. One explained Brownian motion and essentially proved atoms were real. One introduced special relativity. And one, the one that would eventually win him the Nobel Prize, explained a strange experimental result called the photoelectric effect. The puzzle was this. When you shine light onto certain metals, electrons fly off the surface. That had been observed since the 1880s, but the pattern of the results was bizarre by any classical account. If light is a wave, which Maxwell had shown convincingly, then brighter light should knock electrons off with more energy. More intensity, bigger wave, harder impact. That is what you would expect. But that is not what happens. What actually happens is that the energy of the ejected electrons depends on the color of the light, not its brightness. Dim violet light produces high-energy electrons. Bright red light may produce no electrons at all, regardless of how intense you make it. Brightness only changes how many electrons come off, not how fast each one moves. Classical wave theory had no answer for this. None at all. Einstein's explanation was bold and clean. He proposed that light itself travels as discrete packets of energy, not just that atoms absorb it in chunks as Planck had suggested, but that light in flight out in space between source and detector exists as individual particles. Each one carrying an energy equal to Planck's constant multiplied by the frequency of the light. A violet packet carries more energy than a red one because violet light oscillates faster. When one of these packets strikes an electron in a metal, it is a one-on-one collision. One packet, one electron. If the packet carries enough energy to break the electron free, if not, nothing happens. No number of weak packets will substitute for one strong one. A million gentle taps will never do what a single firm knock can. This was a far more radical claim than Planck had made. Planck had quantized the behavior of matter. Einstein was quantizing light itself. That electromagnetic radiation which Maxwell had shown was a continuous wave, and which had been confirmed as a wave by decades of experiment, also behaves as a particle. That it comes in lumps. Even Planck was skeptical. When he wrote a letter recommending Einstein for membership in the Prussian Academy of Sciences in 1913, he praised Einstein's contributions warmly, but specifically noted that Einstein had occasionally overreached in his speculations and cited the light quantum hypothesis as the example. The man who had introduced quanta in the first place thought Einstein had gone too far with them. He had not. The light quantum was one of the most important ideas in the history of physics. And now something deeply uncomfortable was sitting in the middle of the field. Light was a wave. The evidence was overwhelming and had been for over a century. Thomas Young's double-slit experiment in 1801 had produced interference patterns that only waves can make. Maxwell's equations described light as oscillating electric and magnetic fields. Diffraction, polarization, interference, all of it confirmed wave behavior again and again. And yet Einstein had just shown that light also arrived as particles, knocked electrons around one at a time, and carried energy in discrete bundles that behaved nothing like a smooth, continuous wave. Both things were true. And they appeared to contradict each other completely. This was not a misunderstanding. It was not sloppy language. It was a genuine paradox sitting at the center of physics with no resolution in sight. The greatest minds in the field would spend the next 2 decades trying to understand it. Some of them never would. And the discomfort that you might feel right now, trying to picture something that is simultaneously a wave and a particle, is exactly the discomfort that Niels Bohr and Werner Heisenberg and Erwin Schrödinger felt. The universe, it was becoming clear, did not intend to be comfortable. The paradox had a name by now. Wave-particle duality. And naming it did not solve it. It just gave physicists something to argue about more precisely, because the double-slit experiment, the one Thomas Young had performed in 1801 to demonstrate that light was a wave, now sat in an entirely new and troubling light. Young had shown light through 2 narrow slits in a barrier and watched it land on a screen behind. What appeared was not 2 bright bands, which is what you would expect from particles flying through 2 openings. What appeared was a pattern of alternating bright and dark stripes, a zebra of light and shadow that could only be explained by waves interfering with each other, where 2 wave crests arrived together, brightness, where a crest met a trough, darkness. It was as clean a demonstration of wave behavior as physics had ever produced. And yet Einstein was saying each of those wave crests was actually made of individual particles, photons, each one discrete, each one a localized bundle of energy. So what was interfering with what? If photons were particles, which photon was interfering with which other photon? What was doing the waving? Nobody had a good answer. And the experiment, left alone for a century as a comfortable demonstration of wave optics, had suddenly become a source of profound unease. Physicists would eventually be able to fire photons one at a time through the double slit, one by one, too slowly to possibly interfere with each other, and the interference pattern would still appear, built up dot by dot over thousands of individual detections. Each photon arriving alone, somehow interfering with itself, passing through both slits simultaneously as a wave, arriving at the screen as a particle. The discomfort never really went away. It just became familiar. But in 1905, that single photon version of the experiment was still in the future. What physicists had right now was a contradiction embedded in their most successful theories and no obvious way to reconcile it. And before they could even begin to address that, a new crisis arrived. One that made the wave-particle problem look almost manageable by comparison. It came from inside the atom itself. By the early 1900s, physicists knew that atoms existed, which had not always been obvious. They knew atoms contained electrons, since J.J. Thomson had discovered the electron in 1897. Thomson's model of the atom placed electrons embedded in a diffuse fierce positive charge, like raisins in a pudding. It was a reasonable first guess. It was also completely wrong, and the man who proved it was a broad-shouldered, booming-voiced New Zealander named Ernest Rutherford. Rutherford set up his experiment in Manchester in 1909. He and his collaborators Hans Geiger and Ernest Marsden fired tiny positively charged particles, alpha particles, essentially helium nuclei stripped of their electrons, at an extraordinarily thin sheet of gold foil. The foil was only a few hundred atoms thick, and if Thomson's model were correct, those alpha particles should have passed through it with only minor deflections. The positive charge of the atom would be spread out thinly enough that there would be nothing dense enough to deflect a fast-moving particle significantly. Like firing bullets through fog, most of them did exactly that. They passed straight through or deflected only slightly, just as Thomson's model predicted. But some did not. A small fraction deflected at large angles, and a tiny shocking number bounced almost straight back toward the source. When Rutherford heard Geiger's description of the backscattering results, he reportedly said it was as if you had fired artillery shells at tissue paper, and they had come back and hit you. The comparison was his own, and it was accurate. Rutherford spent months working through the mathematics. The conclusion was unavoidable. Almost all of the atom's mass and all of its positive charge had to be concentrated in a region fantastically small compared to the atom as a whole. He called it the nucleus, and the numbers were staggering. If you scaled the atom up to the size of a large sports stadium, the nucleus would be a marble on the field at the center. Everything else was empty space. The atom, the supposedly solid building block of all matter, was almost entirely nothing. He published the nuclear model in 1911. It was immediately compelling. It explained the scattering data with remarkable precision, and it was, according to everything classical physics knew, completely impossible. Here is the problem. You have a tiny, dense, positively charged nucleus sitting at the center. You have negatively charged electrons somewhere around it. Opposite charges attract. Why do the electrons not simply fall inward and crash into the nucleus? The obvious answer, the one Rutherford's model implicitly assumed, is that the electrons are orbiting. Moving fast enough that their inward pull is balanced by the tendency of circular motion to carry them outward, a miniature solar system. Planets surround a sun. But James Clerk Maxwell's equations, the same equations that had been so triumphant in explaining light and electromagnetism, said this could not work. They said it clearly and without ambiguity. A charged particle moving in a circle is constantly accelerating because even if its speed stays constant, its direction is always changing. And any accelerating charged particle must radiate energy as electromagnetic waves, continuously. That is not an approximation. That is a direct consequence of Maxwell's theory. So an orbiting electron would radiate, losing energy, spiraling inward, and crash into the nucleus within roughly 100 millionth of a second. Some calculations put the collapse time at around 10 to the negative 11 seconds. The atom, by classical physics, should not exist, and yet here you are. The atom has been stable for billions of years. Chemistry works. The world is solid. Something was profoundly, fundamentally broken in the classical picture, and nobody knew how to fix it. This is the pressure that a young Danish physicist named Niels Bohr walked into when he arrived in Manchester to work with Rutherford in 1912. Bohr was 26 years old. He had just finished his doctorate in Copenhagen and had come to England hoping to work with J.J. Thomson in Cambridge, but the collaboration had not gone well. Bohr and Thomson had different styles. Bohr was slow, enormously careful, almost geological in how he turned a problem over before committing to a conclusion. Thomson moved faster and was not particularly interested in the reservations of a young newcomer. So Bohr moved north to Manchester, to Rutherford's group, where the crisis of the impossible atom was sitting unsolved on the table. Bohr did something audacious. He did not try to save classical physics. He did not look for a mechanism within Maxwell's equations that would somehow stabilize the orbits. From. Instead, he looked at the problem and said, classical physics simply does not apply here, it fails, and then he wrote down new rules. From. In a series of 3 papers published in 1913, what physicists sometimes call the Great Trilogy, Bohr proposed that electrons could only orbit the nucleus at certain specific distances, certain permitted orbits, and that when they occupied those orbits, they did not radiate. From. Not because some classical mechanism was preventing it, but because that was a postulate, a declared rule of a new and different framework. The electron in a permitted orbit simply does not lose energy. It sits there stably until something happens to move it. Which permitted orbits? From. Here Planck's constant appeared again, the same tiny number from the black body problem 13 years earlier. Bohr said the allowed orbits were the ones where the electron's angular momentum was a whole number multiple of Planck's constant divided by 2 pi. 1 unit, 2 units, 3 units, but nothing in between. From. Quantized again, discrete again, and lumpy. When an electron moved from one permitted orbit to another, it had to absorb or emit a photon carrying exactly the energy difference between those 2 levels. Drop to a lower orbit, emit a photon of that specific energy. From. Absorb a photon of just the right energy, jump to a higher orbit. The permitted energy differences produced photons of very specific frequencies, very specific colors. Now here is what made this more than philosophy. From. For decades, physicists had known that when you heat hydrogen gas and look at the light it emits through a prism, you do not get a rainbow. You get a set of sharp, bright lines at very specific wavelengths with darkness in between, a spectral fingerprint. From. In 1885, a Swiss schoolteacher named Johann Balmer had found a mathematical formula that predicted the positions of those lines with astonishing accuracy. But nobody knew why the formula worked. It was a pattern without an explanation. From. Bohr calculated the energy levels of his permitted orbits for hydrogen, and then calculated the frequencies of photons that would be emitted when electrons jumped between those levels. The numbers matched Balmer's formula almost exactly, not approximately, not roughly. The agreement was extraordinary. From. A theory built on invented postulates that defied classical physics had just predicted the hydrogen spectrum with a precision that decades of prior physics could not touch. When Einstein heard about it, he reportedly said it was one of the greatest discoveries, and he meant it. From. Because this was exactly the kind of result that changes things. You could propose the strangest idea imaginable, but if it predicted what no other framework could, people had to take it seriously. And they did. From. But Rutherford wrote to Bohr almost immediately with a question that cut straight to the heart of the matter. He asked how an electron decided which orbit to jump to, and when. It was a penetrating question. Bohr did not have a satisfying answer. From. The model gave you the energy levels and the transition frequencies, but it gave you no mechanism, no picture of what actually happened during the jump, no explanation for why these particular postulates should be true rather than some other set. It felt like rules handed down from somewhere. From. Rules that worked without explaining themselves, and it had another limitation that became clear quickly. Bohr's model worked beautifully for hydrogen. 1 electron, 1 proton. Clean and tractable. From. But when physicists tried to extend it to helium, with 2 electrons or to any more complex, fell apart. The spectral lines of heavier elements did not match what the model produced. The key that opened hydrogen's door fit nothing else. So by 1913, the situation was this. From. 2 separate crises, each unresolved. Light was behaving as both wave and particle with no coherent picture of how, and atoms were stable in a way that classical physics said was impossible, explained by a model that worked only for the simplest case and offered no deeper reason for its own success. From. The physics of the very small had 2 sets of working rules that nobody could justify and no framework that unified them. A deeper theory was needed. Something more general, something with real foundations. From. And finding it would take another decade and would require some of the most intense and concentrated intellectual work in the history of science, carried out by a generation of young physicists who were not yet famous, working in rooms that smelled of chalk dust and ambition, on islands swept by North Sea wind and from. In alpine retreats whose other details history has chosen to leave somewhat vague. The decade between Bohr's 1913 papers and the mid-1920s was one of the strangest periods in the history of physics. The tools worked. The Bohr model predicted hydrogen spectrum. From. Einstein's photon explained the photoelectric effect. Planck's constant kept appearing in every successful calculation, but nobody understood why any of it worked. The quantum rules were recipes without a kitchen, results without a mechanism. And the physicists who were most honest about this were also the most unsettled by it. What was needed was not another clever patch. What was needed was a genuine new mechanics. Something to replace Newton's laws at the atomic scale the way Einstein's relativity had replaced them at high speeds and strong gravitational fields. A complete framework, not a collection of borrowed assumptions and improvised postulates. And the person who took the first decisive step toward that framework was not one of the established figures. He was a 22-year-old German with hay fever and an extraordinary tolerance for mathematical discomfort. Werner Heisenberg grew up in Munich, the son of a professor of Byzantine history. He had been a precocious student who read Plato in the original Greek for recreation and who once solved a problem during a doctoral examination so impressively that his examiner, the great experimental physicist Wilhelm Wien, was reportedly stunned. By 1925, he was working as an assistant to Max Born in Göttingen, one of the main centers of European theoretical physics, and he had been thinking for months about what a proper quantum theory would have to look like. His starting point was a conviction that would shape everything that followed. He thought that a legitimate theory of atomic physics should be built only from quantities you could actually measure, not from pictures, not from models, not from imagined trajectories. In classical physics, you could talk about the position of an electron at every moment along its orbit, the path it traced through space, but nobody had ever observed an electron doing that. What you could observe were the frequencies and intensities of the spectral lines that atoms produced. So Heisenberg decided that a proper theory should be built from those observables and from nothing else. In June of 1925, his hay fever was so severe that he asked for leave from Göttingen and took a boat to Helgoland, a small rocky island in the North Sea with almost no vegetation and almost no pollen. He rented a room from a local woman and walked along the cliffs in the evenings and worked through the nights. And there, alone on that wind-swept island, he constructed what would become the first complete formulation of quantum mechanics. His approach involved arranging numbers that described atomic transitions into mathematical tables and then working out the rules for how those tables should combine. He was not thinking of electrons as small planets. He was thinking of transitions, of the relationships between energy states, of the probabilities associated with jumps from one level to another. The mathematics was unfamiliar and disorienting, and when he worked out how to multiply two of his tables together, he found something that disturbed him deeply. The result depended on the order of the multiplication. If he multiplied table by table B, he got a different answer than if he multiplied table B by table A. In ordinary arithmetic, 3 times 5 equals 5 times 3, but Heisenberg's quantities did not behave that way. The order mattered. He later said he was so troubled by this result that he stayed up most of the night checking his calculations. When he had confirmed them, he walked out to the tip of the island to watch the sunrise over the North Sea. He knew he had found something. He was not sure what. When he brought the work back to Göttingen, Max Born looked at it and recognized the mathematical structure immediately. Heisenberg had, without knowing it, reinvented matrix algebra. The tables were matrices, and the fact that matrix multiplication does not commute, that the order matters, was a known property of that mathematical system. Born and his student Pascual Jordan worked with Heisenberg to formalize the theory into a complete and self-consistent framework, which came to be called matrix mechanics. It was the first rigorous formulation of quantum mechanics, and it worked. It reproduced the hydrogen spectrum. It handled the intensities of spectral line, not just their positions. It gave numbers that matched experiments with extraordinary precision, and almost nobody could use it. The abstraction was nearly impenetrable. There was no picture, no model, no physical intuition to grab onto. Just arrays of numbers and algebraic rules that operated on quantities most physicists had never encountered. Even those who could follow the derivations found it difficult to feel that they understood what was happening physically. Matrix mechanics was correct, and it was almost impossible to think with. Then, in the winter of 1925 and spring of 1926, something happened that changed the atmosphere of the entire field. A completely different route to the same destination appeared, built by a man who was not trying to abandon physical intuition but to preserve it. From Erwin Schrödinger was 38 years old, older than most of the quantum revolutionaries, an Austrian with a wide-ranging intellect that encompassed philosophy and poetry as well as physics. He had read Louis de Broglie's doctoral thesis from 1924, the one proposing that electrons had a wavelength, that matter waves were real, and Schrödinger found the idea beautiful. If electrons were waves, he reasoned, then there had to be a wave equation governing them, just as Maxwell's equations governed electromagnetic waves and the classical wave equation governed vibrations on a string. He set out to find it. In December of 1925, he went on a holiday to a villa in Arosa in the Swiss Alps, bringing a woman whose identity history has never definitively established. During the weeks that followed, circumstances that have fueled considerable academic gossip, he derived the equation that now carries his name. The Schrödinger equation describes how the quantum wave function, usually written with the Greek letter psi, evolves through time. It is a differential equation, the kind of mathematics that physicists had been using for centuries to describe how waves propagate through fluids and solids and fields. For the first time since Planck had introduced the quantum in 1900, the new physics looked like something classical physicists could recognize. When Schrödinger's papers appeared in early 1926, the response was immediate and enthusiastic. Here was something you could actually visualize. The wave function could be imagined as a real physical wave, smearing the electron's presence across a region of space rather than placing it at a precise point. You could picture it, you could calculate with it. And it gave the same answers as Heisenberg's matrices for every problem anyone tested. The hydrogen spectrum, again. The energy levels of simple systems, again. The match with experiment was exact. Now there were two apparently different theories, both giving the same predictions. Schrödinger showed in 1926 that the two formulations were mathematically equivalent. Matrix mechanics and wave mechanics were two languages for the same underlying structure, the way a circle can be described in Cartesian or polar coordinates. Paul Dirac, an almost preternaturally quiet British physicist who combined mathematical elegance with an economy of words that bordered on the uncanny, would later unify both into a more general framework, but that unification came after a more immediate problem demanded attention. If the Schrödinger equation described the electron as a wave, what was actually waving? Schrödinger himself believed the wave function was a physically real thing. The electron was literally spread out in space, smeared across a region according to the shape of the wave function. When you detected it at a particular point, that was the wave collapsing or concentrating, a real physical process involving a real physical wave. Max Born looked at this picture and found it untenable. In 1926, he proposed a different interpretation, one that was far more radical and far more troubling. He said the wave function does not describe a real wave of electron stuff spread through space. What it describes is probability. Specifically, the square of the wave function at any point in space gives you the probability of finding the electron at that point if you make a measurement. The wave function is a probability wave, a mathematical object encoding your knowledge of what might happen, not a physical object describing what is happening. This distinction sounds technical. It is not. It is one of the most profound claims ever made about the nature of reality. In classical physics, probability was always a measure of ignorance. If you do not know where a marble rolled under the sofa, you assign probabilities to different locations. But the marble is somewhere. It has a definite position you simply have not determined. Born was saying that for an electron, before you measure it, there is no definite position. Not unknown, but non-existent. The probability is not a reflection of your ignorance about a pre-existing fact. The probability is the fact. The electron does not have a location until the measurement happens. The measurement does not reveal where it was. The measurement determines where it is. And here is the consequence that made this genuinely shocking. If probability is built into the bedrock of nature, if the universe is fundamentally random at the smallest scale, not because we lack information but because there is no information to have, then physics has a new and permanent relationship with uncertainty. From the clockwork universe of Newton, deterministic, predictable in principle, given sufficient information about initial conditions, was not merely an approximation. It was, at the atomic scale, simply wrong. Schrödinger was not satisfied with this. He would spend years trying to recover a picture of electrons as real waves with real locations, and he was not alone in his dissatisfaction. The man who had done more than almost anyone to open the quantum era, the patent clerk from Bern who was by 1926 widely regarded as one of the 2 or 3 greatest living physicists, held to a deep and principled conviction that Born's probabilistic interpretation could not be the final word. That nature, at its deepest level, had to be deterministic. That particles had to be somewhere, doing something specific, whether or not anyone was measuring them. Albert Einstein had not, of course, stopped thinking about quantum mechanics. He had helped to create it. He understood it as well as almost anyone. And he believed it was incomplete. Not wrong exactly, but missing something, leaving something out. The argument that was about to unfold between Einstein and Niels Bohr would last for decades, would be fought across conference tables and in published papers and in long letters that crossed the Atlantic by steamship, and would ultimately be resolved not by philosophy but by an experiment that neither man lived to see performed. But before that battle could begin in earnest, one more piece had to fall into place. One more idea so strange that even the physicist who produced it found it almost impossible to absorb. It came from Heisenberg again, working in Copenhagen in 1927, and it placed a hard and permanent limit on what could ever be known about any quantum system, not because of any failure of instruments or any gap in technique, but as a fundamental feature of the universe itself. Heisenberg's uncertainty principle arrived in 1927, and it arrived not as a philosophical opinion but as a mathematical result derived from the structure of the new quantum mechanics itself. The argument was precise and inescapable. If you want to know the position of a particle very accurately, the act of measuring it necessarily disturbs its momentum by a large and unpredictable amount. If you want to know its momentum very accurately, its position becomes correspondingly uncertain. The more precisely you pin down one quantity, the more completely the other dissolves. And this is not a statement about clumsy instruments or insufficient technology. It is a statement about the universe. The product of the uncertainty in position and the uncertainty in momentum can never be smaller than a fixed quantity, roughly equal to Planck's constant divided by 4 pi. Nature has written a minimum ignorance into its own laws, and no engineering improvement will ever erase it. Heisenberg illustrated the principle with a thought experiment that became famous. Imagine trying to see an electron by shining light on it. To see something, you need photons to bounce off it and reach your eye or your detector. But a photon carries momentum. When it bounces off an electron, it kicks the electron, changing the electron's momentum by an unpredictable amount. Use high-frequency light, short wavelength, and you can locate the electron precisely because the wavelength sets the resolution. But a high-frequency photon carries more momentum, so the kick it delivers is larger and more disruptive. Use low-frequency light, and the kick is gentler, but the long wavelength blurs the position measurement. No matter what you do, the product of the two uncertainties remains bounded below by Planck's constant. The act of observing disturbs the thing observed, and the disturbance is not a solvable engineering problem. It is the minimum cost of knowledge. This had consequences that reached far beyond any single experiment. It meant that the classical ideal of complete knowledge, the idea that if you knew the position and momentum of every particle in the universe you could in principle predict all future events, was not merely impractical. It was forbidden. The universe did not permit that level of knowledge even in principle. Determinism, the philosophical backbone of Newtonian physics, was not defeated by the limits of human instruments. It was defeated by the structure of reality. When Heisenberg published his uncertainty paper in March of 1927, the reaction in the physics community was not uniform. Some found it liberating. If you restricted quantum mechanics to observable quantities and stopped asking what particles were doing between measurements, the theory worked perfectly, and the uncertainty principle explained why classical intuitions broke down at small scales. Others found it deeply unsatisfying for exactly the same reasons that made it acceptable to the first group. A theory that refused to tell you what was happening when nobody was looking felt less like physics and more like a surrender. From Bohr had his own interpretation of the uncertainty principle, one that went even further than Heisenberg's. Bohr argued that concepts like position and momentum were not properties that particles possessed independently. They were properties that only existed in the context of a specific measurement. Before you decided whether to measure position or momentum, the particle did not have either in any definite sense. This was the core of what Bohr called complementarity. Position and momentum were complementary descriptions. You could access one or the other depending on your experimental arrangement, but never both simultaneously. And the reason was not that nature was hiding the other quantity. It was that the question of both simultaneously was simply not well formed. It was asking something that had no answer because it was asking the wrong kind of question. This view, combined with Born's probabilistic interpretation and Heisenberg's uncertainty principle, formed the nucleus of what came to be known as the Copenhagen interpretation. Copenhagen, because Bohr's institute there was the intellectual center of the effort to codify what quantum mechanics actually meant. The Copenhagen position, stated carefully, was something like this: the wave function contains everything that can be known about a quantum system. Measurements produce definite results according to the probabilities encoded in the wave function. Between measurements, it is not meaningful to ask what the system is doing or what properties it has. The theory is complete. There is no deeper layer underneath. This was the mainstream view by the time of the Fifth Solvay Conference in Brussels in October of 1927, and that conference is worth dwelling on for a moment because the photograph taken there is one of the most extraordinary documents in the history of science. 29 physicists gathered around tables in a Brussels hotel. Bohr is there, Heisenberg is there, Born, Schrödinger, Dirac-Pauli, de Broglie, Lorentz, Curie. 17 of the 29 participants were or would become Nobel laureates, and at the center of that photograph, seated in the front row, was Einstein. Watching, listening, deeply skeptical, and preparing his counteroffensive, Einstein had not accepted the Copenhagen interpretation. He did not reject quantum mechanics as a practical tool. He had helped build it. He knew perfectly well that the Schrödinger equation worked, that Born's rule gave correct predictions, that the uncertainty principle was confirmed by every experiment. What he rejected was the claim that this was the complete story. He believed that particles had definite properties, whether or not they were being measured, that the moon did not cease to exist or to have a location, simply because no one was looking at it, and that any theory that refused to answer questions about what was happening between measurements was not a finished theory. It was an unfinished one. At Solvay, Einstein began presenting thought experiments designed to show that the Copenhagen interpretation led to internal contradictions. These were not casual objections. They were carefully constructed arguments, each one targeting a specific feature of the Copenhagen framework. Bohr answered them one by one, sometimes immediately, sometimes after hours of intense thought. The exchanges between them were legendary even to the other physicists present. Einstein would present his argument at breakfast. Bohr would be visibly troubled by mid-morning. By evening, Bohr would have found the flaw. And the next morning, Einstein would arrive with a new one. The 1930 Solvay Conference brought what many considered Einstein's most powerful attack. He proposed the photon box thought experiment, a box with a shutter controlled by a precise clock designed to release a single photon at a known moment. You weigh the box before and after. By Einstein's own equation relating energy and mass, the tiny decrease in mass tells you the energy of the escaped photon exactly. Since you also know precisely when it left, you seem to know both the energy and the timing with arbitrary precision, violating the energy-time uncertainty relation. Bohr was reportedly distressed that evening. This one was harder than the others. But by the next morning, working through the night, he had found the answer, and the answer was a knife turned in Einstein's own hand: general relativity. When you weigh the box, it moves in Earth's gravitational field. And according to Einstein's own theory of general relativity, a clock moving in a gravitational field runs at a different rate depending on its position. The tiny displacement of the box during weighing introduces uncertainty in the clock reading, and that uncertainty, when calculated precisely, turns out to be exactly large enough to preserve Heisenberg's principle. Einstein had been defeated by his own theory of gravity. Bohr later said he found this episode deeply moving, that Einstein's own greatest work had become the instrument of his defeat. But Einstein did not concede. He acknowledged that Bohr's response was correct in its details. He accepted that no logical contradiction had been found. What he refused to accept was the conclusion that Copenhagen drew from this. He shifted his objection. He stopped trying to show that quantum mechanics was internally inconsistent and began arguing instead that it was incomplete, that it failed to describe elements of physical reality that genuinely existed. The particles had to be somewhere, the properties had to have values, the theory simply wasn't capturing them. And here is where the story takes a turn that changes its entire character. Because Einstein's objection was not just philosophical. It was pointing at something real. Something that, if you followed it carefully enough, led to a prediction that could actually be tested. Not a thought experiment, not a debating point, a genuine experimental question about the structure of nature. The argument crystallized in 1935 in a paper Einstein wrote with two younger colleagues, Boris Podolsky and Nathan Rosen. The paper asked a single-focused question. Can quantum mechanics be considered a complete description of physical reality? And it answered with a careful, patient argument that the answer was no. At the center of the argument was a phenomenon that Schrödinger, reading the Einstein-Podolsky-Rosen paper, immediately named with a word that would become one of the most important in all of physics. He called it entanglement. And he called it the characteristic trait of quantum mechanics, the one that forced the entire departure from classical thought. Two particles, created together or allowed to interact, can be placed in a joint quantum state such that measuring one of them instantly determines what you will find when you measure the other, regardless of the distance between them. Not because a signal passes between them. Not because one influences the other after the fact, but because their wave functions are not separate things. They are one entangled thing described by a single joint state that cannot be factored into two independent pieces. Einstein, Podolsky, and Rosen argued that this was absurd, or rather that it forced a choice. Either the results of measurements on distant entangled particles were coordinated by pre-existing properties that quantum mechanics simply failed to describe, local hidden variables, properties the particles carried with them from the moment of their creation. Or quantum mechanics required influences that traveled instantaneously across any distance, violating the fundamental principle of special relativity that nothing can travel faster than light. Einstein called the second option spooky action at a distance, and he meant it as a dismissal. It was, he believed, obviously impossible, which meant the first option had to be true, which meant quantum mechanics was incomplete. Bohr published a response later that same year, 1935. It was long, carefully reasoned, and by most accounts not entirely easy to follow. He argued that the EPR argument misused the concept of physical reality, that you could not speak of the properties of a particle independently of the experimental context in which those properties would be measured. His answer satisfied many physicists, but not all, and it did not satisfy Einstein. The debate appeared to have reached an impasse. Two positions, each internally consistent, producing the same experimental predictions and no obvious way to distinguish between them. What nobody in 1935 realized was that the impasse was not permanent. That hidden inside the EPR argument was a question that could, in principle, be answered by experiment, not by a thought experiment, by actual measurements in an actual laboratory on actual particles. The key had not yet been found. It would take another 3 decades, and it would come not from one of the famous names, but from a quietly brilliant Irish physicist sitting at a desk at CERN, turning the EPR argument over in his mind with the patient attention it deserved, until he saw something that everyone else had missed. John Stuart Bell was not famous. That is the first thing to understand about him. He was a staff physicist at CERN, the European Particle Physics Laboratory near Geneva, working primarily on accelerator design and particle beam theory. He was Irish, born in Belfast in 1928, the son of a horse dealer, the first in his family to attend university. He was thoughtful and careful and not given to self-promotion. And for years, his interest in the foundations of quantum mechanics was something he pursued privately, almost secretly, because the foundations of quantum mechanics were not considered a respectable research topic in the 1950s and 60s. The theory worked. The calculations matched the experiments. Asking what it all meant underneath was regarded by philosophical indulgence, a distraction from real science. Bell disagreed, but he kept that disagreement mostly to himself. What he had been turning over in his mind quietly for years was the EPR argument. Einstein, Podolsky, and Rosen had published it in 1935, and it had been generating philosophical debate ever since. But Bell saw something in the argument that the philosophical debate had missed. He saw that the choice between quantum mechanics and local hidden variables was not merely a matter of taste or interpretation. It was, in principle, an empirical question. You could test it. Not by finding a contradiction in the mathematics, which Bohr had successfully resisted for decades, but by designing an experiment whose statistical outcomes would differ, depending on which view was correct. The key insight was deceptively simple. If particles carry hidden variables, definite pre-existing values for all their properties, then the correlations between measurements on separated entangled particles must obey certain statistical constraints. Those constraints followed from very basic assumptions about locality and realism, from the idea that the result of a measurement on one particle could not depend on what measurement was chosen for the other particle, far away. Bell derived an inequality, a mathematical bound that any local hidden variables theory must satisfy. If you measured the correlations between entangled particles along different axes and combined those correlations in a specific way, the result, according to any local realistic theory, could not exceed a certain value. Bell published this result in 1964 in a journal called Physics, which was a relatively obscure publication at the time, and the paper received little immediate attention. But what Bell had done was extraordinary. He had taken an argument that had been stuck in philosophy for nearly 30 years and turned it into physics. He had drawn a line in the sand and said, nature is on one side or the other. Either the correlations between entangled particles stay within the bounds required by local hidden variables, or they exceed those bounds, in which case local hidden variables are ruled out, and quantum mechanics is right not just as a calculating tool but as a description of something genuinely non-local in the structure of reality. The question was no longer which interpretation you preferred. The question was what the universe actually did. Now the experiments had to be performed. And that took time because performing them correctly was extremely difficult. You needed a reliable source of entangled particles. You needed detectors efficient enough to catch a statistically meaningful fraction of them. You needed to measure the correlations along multiple different angles with enough precision to distinguish a violation of Bell's inequality from a result that merely approached it. And you needed to close the loopholes, the various ways an experiment could produce misleading results, not because of quantum mechanics or hidden variables, but because of technical imperfections. The first serious attempts were made in the early 1970s by Stuart Friedman and John Clauser at Berkeley. Their results favored quantum mechanics over local hidden variables, but the experiment had limitations that left room for argument. A more definitive test came in the early 1980s from a physicist named Alain Aspect working at the Institut d'Optique at the Université Paris-Sud in Orsay. Aspect's experiment used pairs of photons emitted by calcium atoms that had been excited by laser light. The photons flew off in opposite directions and were each directed toward a polarization measurement station. The angle of the polarization measurement could be changed rapidly, and Aspect's crucial innovation was to change the measurement settings while the photons were already in flight, fast enough that neither photon could have sent any signal to the other about what measurement it was about to face, even traveling at the speed of light. This closed what is called the locality loophole. It ensured that if correlations appeared, they could not be explained by any signal passing between the two measurement sites within the time available. The results from Aspect's experiments, published in 1981 and 1982, were unambiguous. Bell's inequality was violated. The correlations between the entangled photons were stronger than any local hidden variables theory could produce. From. They matched the predictions of quantum mechanics precisely. The universe was not operating according to local realism. Something about the behavior of entangled particles defied the assumptions that Einstein had considered non-negotiable. Let that settle for a moment. This was not a small result. From. This was one of the most consequential experimental findings in the history of physics. The debate that had run from the 1927 Solvay Conference through 30 years of philosophical argument was not, in the end, a philosophical question. It had a factual answer. From. And the answer was that Einstein's intuition about hidden variables, his conviction that particles must carry definite properties from the moment they are created, and that quantum mechanics simply failed to capture those properties, was wrong. Not approximately wrong. From. Not wrong in a technical way that might be salvaged by a cleverer formulation. Wrong in a way that the universe itself had enforced. But here is where the pivot deepens, because ruling out local hidden variables does not by itself tell you what is true. It tells you what cannot be true. From. The question of what quantum mechanics actually means, what is really happening when entangled particles produce these correlations, remained as open as ever. And the range of possible answers was stranger than most people outside physics appreciated. One possibility was to keep hidden variables but abandon locality. From. David Bohm had developed exactly such a theory in 1952. Bohm's mechanics, sometimes called pilot wave theory, was a fully deterministic framework in which particles had definite positions at all times, guided by a wave that influenced their motion instantaneously across any distance. From. Every prediction of standard quantum mechanics was reproduced exactly, but the guidance was non-local. The wave connecting a particle to its distant entangled partner was not a signal that traveled through space. It was a feature of the wave function of the whole system, acting everywhere at once. From. Bell's theorem did not rule this out. Non-local hidden variables were still permitted. What was ruled out was local hidden variables, the combination of definite pre-existing properties and no faster-than-light connections. A second possibility was the Copenhagen view, essentially unchanged. From. Particles did not have definite properties until measured. The wave function was a complete description. Measurement created the definite outcome. From. Entanglement produced correlations because entangled particles shared a single wave function. Not because they communicated, but because they were never truly separate things in the first place. From. Copenhagen handled Bell's results without difficulty, because Copenhagen had never claimed that particles had definite properties between measurements. The violation of Bell's inequality was expected, not surprising. From. A third possibility was considerably stranger, and it had been proposed back in 1957 by Hugh Everett, a graduate student at Princeton. Everett's idea was that the wave function never collapsed. From. That every time a quantum measurement was made and the outcome appeared to be one definite result, every other possible outcome also occurred in a branching structure of equally real worlds. In one branch, the photon was detected with horizontal polarization. From. In another branch, simultaneously and equally real, it was detected with vertical polarization. There was no collapse because there was no need for one. Everything that could happen did happen. You experienced one outcome simply because you were one observer in one branch. From. The other branches were equally real and equally inhabited by versions of you having other experiences. Everett called this the relative state formulation. Others called it the many worlds interpretation. From. It was largely ignored for years, then slowly taken more seriously, and today it has a significant following among physicists and philosophers who find it conceptually cleaner than Copenhagen, despite the extraordinary ontological price tag. From. It solves the measurement problem by eliminating the collapse, but it does so by populating an inconceivably vast branching reality with copies of every observer, every outcome, every quantum event that has ever occurred. From. What Bell's theorem and aspects experiments did to all of these interpretations was remarkable in a subtle way. They did not decide between them. From. Copenhagen, Bohm's pilot wave, Everett's many worlds, and several other interpretations all make the same experimental predictions, and all predict violations of Bell's inequality in exactly the way observed. The experiments ruled out local hidden variables, but they left the interpretive question fully open. From. What they changed was the frame of the debate. Before aspect, you could believe, as many physicists did, that the interpretation question was purely philosophical, that there was no fact of the matter, and no experiment could ever bear on it. After aspect, that position was harder to hold. The experiments had demonstrated that at least one feature of the interpretive landscape, local realism, was empirically false, which meant the other features might also be empirically decidable, given the right questions and the right experiments. The fallout from this was not immediate, but it was significant, and it kept compounding. Because once you accepted that entanglement was real, that the correlations it produced were genuine features of nature and not artifacts of incomplete information, the next question became urgent. What could you do with it? The answer, which began to emerge in the 1980s and accelerated dramatically through the 90s, was not what anyone had expected. Entanglement was not just a source of philosophical puzzlement. It was a resource. A physical resource that could be deliberately created, controlled, manipulated, and exploited to do things that were simply impossible in a classical universe. Things like transmitting quantum states from one place to another without physically moving the particle carrying those states. Things like generating cryptographic keys whose security was guaranteed not by the hardness of a mathematical problem but by the laws of physics themselves. And things like building computers that operated on fundamentally different principles from anything that had existed before, machines that could solve certain classes of problems exponentially faster than any classical device. None of this was visible in 1982 when Aspect published his results. What was visible was a clean experimental answer to a question that had been debated for nearly half a century. Local realism was false. The universe was stranger than Einstein had been willing to accept. And the theory that he had helped to build, the theory whose implications he had spent 30 years resisting, had been vindicated not just as a calculation tool, but as a description of something genuinely true about how nature behaved at its most fundamental level. Einstein died in 1955. Bell published his theorem in 1964. Aspect's experiments were completed in 1982. The conversation that began at the 1927 Solvay conference reached its experimental resolution 27 years after the man who started it was gone. And the resolution opened doors that would have astonished everyone in that famous photograph, because what lay behind them was not just a deeper understanding of atoms and photons. It was an entirely new conception of what computation was, what communication was, and what was possible in a universe governed by quantum rules. The practical consequences of that philosophical argument, that long, slow battle over the meaning of a wave function, were about to become some of the most transformative technologies in human history. The first consequence was a shift in what physicists were permitted to think about seriously. Before Bell's theorem and before Aspect's experiments, working on the foundations of quantum mechanics carried a real professional cost. It was the kind of research that could get you labeled as a philosopher rather than a physicist, which in most departments was not a compliment. The attitude among the mainstream was roughly this: the equations work, the predictions match, the interpretation is a matter of personal taste, and spending your career on personal taste is not doing physics. This was not a fringe view. It was the consensus position at most major research institutions throughout the 1950s and 60s. Bell himself had felt this pressure acutely. He worked on foundations only in his spare time, treating it as a hobby conducted alongside his real professional responsibilities at CERN. He was careful about when and how he brought it up with colleagues. The subject had a stigma, and the stigma had real consequences. Young physicists who expressed too much interest in questions about the meaning of wave functions or the reality of quantum states were quietly advised by their supervisors to find a more productive focus. The field self-selected away from foundational questions, and for decades that self-selection was remarkably effective. Aspect results began to erode that consensus, but slowly and unevenly. The immediate response in the physics community was not a dramatic collective awakening. Most working physicists noted the results, filed them under confirmation of quantum mechanics, and continued with their research. The violation of Bell's inequality was not surprising to anyone who had trusted the theory. What was more interesting to the minority who were paying close attention was the implication that entanglement was a real physical phenomenon with experimentally accessible properties, not just a mathematical curiosity embedded in the formalism. From that minority grew through the 1980s as a new generation of physicists began asking what entanglement could actually do. And the first serious answer came not from a physicist concerned primarily with foundations, but from a computer scientist and physicist named Peter Shor, and before him from a physicist named Richard Feynman, who in 1981 at a conference at MIT gave a talk that planted a seed that would take a decade to germinate. Feynman's argument was characteristically direct. He pointed out that simulating quantum systems on classical computers was fundamentally inefficient. The state of a quantum system with many particles had to be tracked as a superposition of exponentially many classical states simultaneously. As the number of particles grew, the computational resources required grew exponentially with them. Even the most powerful classical supercomputer would be overwhelmed by a quantum system containing only a few dozen interacting particles. But a computer that was itself quantum mechanical, one that operated on superpositions and used entanglement as a computational resource, could simulate quantum systems naturally, matching the complexity of the simulated system rather than the exponential blow-up. Feynman was not describing a specific machine. He was describing a horizon, something that should exist if the laws of physics allowed it. The theoretical framework for what such a machine would look like was developed over the following years. David Deutsch at Oxford published a paper in 1985 describing a universal quantum computer, a theoretical device that could simulate any physical process and on which any computation could in principle be performed. Deutsch's machine used quantum bits, qubits, that could exist in superpositions of 0 and 1 simultaneously and could be entangled with each other in ways that had no classical analog. The power of such a machine came not from running faster in the conventional sense, but from the ability to explore multiple computational paths simultaneously, exploiting interference to amplify the paths that led to correct answers and cancel the paths that did not. Then in 1994 came the result that changed everything about how governments, intelligence agencies, and financial institutions thought about quantum computing. Peter Shor, working at Bell Labs, published an algorithm for factoring large numbers that ran on a quantum computer in polynomial time. This requires some unpacking because the implications are enormous. The security of most modern encryption rests on a simple asymmetry. Multiplying two large prime numbers together is easy. Any computer can do it instantly, but given only the product, finding the two original prime factors is computationally hard. Not hard in the sense of requiring careful work. Hard in the sense that the time required grows exponentially with the size of the number. For numbers large enough to be used in cryptography, factoring them on a classical computer would take longer than the current age of the universe. This hardness is the foundation of RSA encryption, which secures bank transactions, government communications, private medical records, and the overwhelming majority of sensitive data transmission worldwide. Shor's algorithm demolished this foundation. On a sufficiently powerful quantum computer, it could factor those same numbers in a time that grew only as a polynomial function of their size, not instantly, but in principle within hours or days rather than billions of years. The encryption protecting the global financial system, classified communications, personal data, and critical infrastructure was vulnerable to a machine that did not yet exist, but that nothing in the laws of physics prevented from existing. The reaction from government and intelligence agencies was not public, but it was real. The National Security Agency in the United States had been tracking quantum computing research since the early 1990s, and Shor's algorithm elevated the subject from theoretical interest to strategic priority. Funding for quantum information science increased. Research programs that had previously operated on shoestring academic budgets began attracting government investment. The question was no longer whether quantum computing was interesting. It was whether the current global cryptographic infrastructure had an expiration date, and if so, how long it had. The physics community responded along two parallel tracks. One track was to accelerate the development of actual quantum computers, to build the hardware that would make Shor's algorithm physically realizable. The other track was to develop new cryptographic systems that would be secure even against quantum attacks. From both tracks were urgent and both required resources and coordination that had not previously been directed at either problem. From the cryptographic response eventually produced what is called post-quantum cryptography, a set of encryption schemes based on mathematical problems that are believed to be hard even for quantum computers. Lattice-based cryptography, hash-based signatures, code-based cryptography. From the mathematics underlying these schemes is different from RSA. Instead of relying on the difficulty of factoring, they rely on geometric structures in high-dimensional spaces, or on the properties of error-correcting codes, problems for which no quantum algorithm offering significant speed-up is currently known. From the United States National Institute of Standards and Technology ran a years-long evaluation process to select and standardize post-quantum algorithms, and published its first finalized standards in 2024. From the transition away from RSA and similar schemes is happening now, not because quantum computers capable of breaking them exist yet, but because encrypted data captured today could be decrypted in the future once such computers arrive, a threat model that intelligence agencies call harvest now, decrypt later. From meanwhile, the hardware track was developing along multiple competing approaches, each with its own physics and its own set of challenges. From the approach that attracted the most early attention and that companies like IBM and Google eventually pursued most aggressively, used superconducting circuits cooled to temperatures near absolute zero to create artificial quantum systems whose energy levels could serve as qubits. From the engineering involved was formidable. The circuits had to be fabricated with nanometer precision. The cooling systems had to reach temperatures colder than the surface of the moon. Every component had to be shielded from electromagnetic interference. From and even under ideal conditions, the quantum states decohered in microseconds far too quickly for long computations. A different approach used actual atoms as qubits, trapped in electromagnetic fields inside vacuum chambers and manipulated with precisely tuned laser beams. From trapped ion quantum computers had longer coherence times than superconducting systems, sometimes holding quantum states for seconds rather than microseconds, and the operations performed on them had higher fidelity, meaning fewer errors per gate. The trade-off was speed. From laser operations on ions were slower than microwave pulses on superconducting circuits, and scaling up to large numbers of ions was technically challenging. A third approach, pursued most prominently by Microsoft, was based on an entirely different physical object. From topological quantum states, specifically a kind of quasi-particle called a non-abelian enneon, predicted by theory to exist in certain exotic materials under the right conditions. The appeal of topological qubits was that the information encoded in them would be protected from local disturbances by its very nature. From the quantum state would be stored in a global property of the system, the topology of a braided path traced by quasi-particles, rather than in a local physical property. Local noise would not be able to disturb the global topology without leaving a detectable signature. From if it worked, error rates would be dramatically lower than in any other approach, potentially making large-scale quantum computing practical far sooner. From the difficulty was that creating and controlling these quasi-particles proved extraordinarily hard experimentally, and Microsoft's timeline for demonstrating a working topological qubit stretched from years into more years without a definitive result. From behind all of these competing approaches was a fundamental challenge that transcended any particular hardware technology. Quantum states are fragile. The environment is constantly interacting with them in ways that collapse superpositions and destroy entanglement. From every stray photon, every thermal vibration, every uncontrolled electromagnetic fluctuation was a source of error. From and unlike classical errors, which could be corrected by simple redundancy, quantum errors could not be corrected by copying, because the no-cloning theorem, derived directly from the linearity of the Schrödinger equation, made it impossible to create an identical copy of an unknown quantum state. From the solution was quantum error correction, and the theoretical framework for it arrived in the mid-1990s. From Shor himself contributed one of the first quantum error-correcting codes in 1995, showing that quantum information could be protected by spreading it redundantly across multiple physical qubits in an entangled state, and that errors on individual physical qubits could be detected and corrected without ever measuring the logical quantum state directly, without collapsing the superposition that the logical qubit was supposed to maintain. The mathematics of quantum error correction was subtle and beautiful, and it drew on the same algebraic structures that underpinned classical error correction, with crucial quantum modifications. But the price was steep. To protect one logical qubit reliably, you needed many physical qubits. Early estimates varied widely, but rough calculations suggested that depending on physical error rates, a single logical qubit might require anywhere from hundreds to thousands of physical qubits. The practical implication was stark. A quantum computer capable of running Shor's algorithm on cryptographically relevant numbers, large enough to actually threaten RSA encryption, would need millions of physical qubits working together with low enough error rates that the error correction kept up with the errors being generated. That was an engineering target whose distance from the state-of-the-art in the 1990s was almost discouraging to contemplate, and yet the field did not slow down, it accelerated. Because the combination of aspects experimental confirmation of entanglement as a real resource, Shor's algorithm as a demonstration of what that resource could accomplish, and the deepening understanding of quantum error correction as a path to fault-tolerant computation had together created a new research landscape that simply had not existed before. Foundations of quantum mechanics, which had been a philosophical backwater for decades, had become one of the most practically consequential research areas in all of science. The question was no longer whether quantum computing was theoretically possible. The question was how hard the engineering would be and how long it would take. The engineering target was daunting, but the field had something that targets rarely have in their early stages. It had a roadmap. Not a complete one, and not one everyone agreed on, but a theoretical framework clear enough to tell you what you needed to build and roughly what it would take to build it. That clarity attracted money, and money attracted talent, and talent began attacking the problem from more angles simultaneously than any single research group could have managed alone. The first serious wave of institutional investment came in the late 1990s and early 2000s, primarily from government agencies that had been startled into attention by Shor's algorithm. In the United States, the Defense Advanced Research Projects Agency DARPA began funding quantum computing research programs. The National Science Foundation expanded its quantum information science portfolio. The Army Research Office supported theoretical work on quantum error correction and quantum algorithms. In Europe, the European Union launched coordinated research initiatives under its framework programs. In the United Kingdom, government investment in quantum technologies grew steadily through the 2000s and accelerated sharply after 2015, when a national quantum technologies program was established with hundreds of millions of pounds in committed funding over 5 years. This was not philanthropy. It was strategic positioning. Every government that understood the implications of Shor's algorithm understood that the nation or alliance that first achieved large-scale, fault-tolerant quantum computation would hold a decisive intelligence advantage over everyone else. The encryption protecting every other nation's classified communications, financial systems, and critical infrastructure would become readable. The stakes were comparable to the development of nuclear weapons in the 1940s, not in destructive capacity, but in the kind of asymmetric advantage that redrew geopolitical power. The difference was that nuclear weapons had required the mobilization of an entire national industrial apparatus. Quantum computing might be achieved by a university group with the right insight and enough time. China recognized this dynamic early and committed to it at a scale that alarmed Western intelligence agencies. In 2016, China launched a quantum satellite called Mesius, named after an ancient Chinese philosopher, into low Earth orbit. Mesius was designed to test quantum key distribution over satellite links, using entangled photons to generate cryptographic keys between ground stations separated by thousands of kilometers. In 2017, the Mesius team announced that they had successfully demonstrated quantum key distribution between stations in China and Austria, a distance of over 7,500 kilometers. The experiment was not a practical communication system. It was a proof of concept. but it was a proof of concept that no other country had achieved at that scale, and it was accompanied by the announcement of plans to build a global quantum communication network with China at its center. The response in Washington was not publicly dramatic, but it was substantive. From congressional appropriations for quantum information science increased. In 2018, the United States passed the National Quantum Initiative Act, which established a coordinated federal program for quantum research and development with an initial authorization of over $1 billion over 5 years. This was followed by executive orders directing federal agencies to begin inventorying their cryptographic systems for quantum vulnerability and to develop transition plans for post-quantum cryptography. The race had become explicit. What made the competitive dynamics particularly complex was that the underlying physics was not secret. The papers describing quantum algorithms, quantum error correction schemes, and experimental techniques for building quantum hardware were published in open scientific literature, available to any researcher anywhere in the world. The field had developed as an academic discipline in the tradition of open science, with preprints shared freely and conferences attended by researchers from multiple countries. Restricting that flow of information would slow down domestic research as much as foreign research, because the domestic researchers depended on the same open exchange. The countermove of classification which had been applied to nuclear weapons research was not obviously available here without sacrificing the science itself. This created a genuine policy contradiction. The government wanted to accelerate domestic quantum research, which required open collaboration and the free movement of talent across institutional and national boundaries. It also wanted to prevent adversaries from benefiting from that research, which required restrictions on collaboration and talent mobility. The two goals were in direct tension and no resolution was clean. Export control regulations were extended to cover some quantum technologies. Visa restrictions on Chinese graduate students in certain fields tightened. But the physics itself could not be classified without hollowing out the research enterprise that produced it. Meanwhile, the private sector had entered the field and was moving faster than any government program. IBM began building superconducting quantum processors and in 2016 made a 5-qubit quantum computer accessible over the cloud through a platform called the IBM Quantum Experience. This was a significant gesture. It meant that any researcher, student, or curious programmer anywhere in the world with an internet connection could write quantum circuits and run them on a real quantum processor. The barrier to entry for quantum computing research dropped dramatically overnight. IBM's stated rationale was to build a community, to develop the software ecosystem, and the human expertise that would be needed when larger and more capable machines became available. The unstated logic was competitive positioning. IBM wanted to establish itself as the default platform for quantum computing before the market existed. Google followed a different strategy. Rather than emphasizing accessibility, Google focused on demonstrating raw capability. In October of 2019, Google published a paper in the journal Nature claiming to have achieved what they called quantum supremacy, a term coined by theoretical physicist John Preskill to describe the point at which a quantum computer could perform a specific task faster than any classical computer. Google's 53-qubit processor, called Sycamore, had completed a particular sampling calculation in about 200 seconds that Google estimated would take the most powerful classical supercomputer roughly 10,000 years. The claim was immediately contested by IBM, who argued that the classical simulation Google had used as a baseline was not optimized and that with better classical algorithms and better use of disk storage, the same calculation could be done in about 2.5 days, not 10,000 years. The debate that followed was technical and partly semantic, hinging on exactly what classical resources you allowed in the comparison. But beneath the specifics, the disagreement pointed at something real. The boundary between what quantum computers could do and what classical computers could not was genuinely blurry, because classical computing was not standing still. Researchers were developing new classical algorithms specifically designed to simulate quantum systems more efficiently, pushing the boundary in the other direction. Every time a quantum computer demonstrated a capability, classical computing researchers asked whether a sufficiently clever classical approach could match it. From this dynamic, the back and forth between quantum demonstrations and classical counters exposed a structural uncertainty in the field that persisted throughout the early 2020s. The question was not whether quantum computers existed. They did. The question was whether they were doing anything that classical computers genuinely could not do, for problems that anyone actually cared about. The tasks on which quantum supremacy had been claimed were not useful computations. They were carefully chosen sampling problems, selected because they were hard for classical computers and tractable for quantum ones, not because anyone needed the answers. The honest summary of the state of quantum computing through the mid-2020s was something like this. The hardware existed but was noisy. The error rates were too high for fault-tolerant computation. The number of physical qubits was too small to implement meaningful quantum error correction, and no quantum computer had yet solved a practically useful problem faster than a classical computer. The potential was enormous and theoretically well established. The engineering distance between that potential and its realization was also enormous and not obviously shrinking fast enough. This gap between potential and realization created a secondary problem, one that began to attract attention from outside the physics community. It was the problem of hype. The combination of genuinely extraordinary theoretical results, genuine experimental progress, and enormous financial and geopolitical stakes created incentives for overstating what had been achieved and understating the distance remaining. Investors who could not evaluate the technical claims directly were presented with narratives in which the breakthrough was always just around the corner. Government officials who needed to justify large appropriations cited each incremental advance as evidence of impending transformation. Startup companies raised hundreds of millions of dollars on business plans whose timelines bore little relationship to what the underlying physics suggested was achievable. The physics community was not entirely innocent in this process. Quantum computing papers routinely described results in language that emphasized progress and potential rather than the persistent severity of the obstacles. The word milestone appeared so frequently in press releases accompanying quantum computing papers that it had effectively lost its meaning. Each new qubit count, each marginal improvement in gate fidelity, each novel error correction demonstration was presented as a step toward a clearly imminent future that kept receding as you walked toward it. The counter voice came from a minority of physicists and computer scientists who were willing to say publicly what many believed privately: that the engineering challenges of building fault-tolerant quantum computers at scale were not merely difficult but possibly prohibitive, that the timelines being discussed in popular accounts were wildly optimistic, and that the gap between current noisy intermediate-scale quantum devices and the fault-tolerant machines needed to run Shor's algorithm on cryptographically relevant inputs might be measured in decades rather than years. Gil Kalai, a mathematician at Hebrew University and Yale, went further than most. He argued on theoretical grounds that quantum computers capable of genuine computational supremacy might be fundamentally impossible, not because the physics was wrong, but because the decoherence problem might be irreducible at scale. His argument was controversial and disputed by most quantum computing researchers, but it represented an important intellectual counterweight in a field where the pressure to maintain enthusiasm was commercially and politically significant. What this created by the early 2020s was a field operating under simultaneous pressures in opposite directions. The theoretical case for quantum computing was as strong as it had ever been. The experimental progress was real and in some areas impressive. The government investment was large and growing. And yet the practical capability remained far short of the promises that had been circulating for nearly 3 decades. The situation was larger, more complex, and more deeply uncertain than the key actors, whether physicists, investors, or policymakers, had been willing to acknowledge in public. And underneath all of that uncertainty, a quieter and in some ways more immediate branch of quantum technology had been advancing steadily, without the drama and the hype, solving real problems with real hardware that already existed, not quantum computing. Something older, less glamorous, and in the near term considerably more reliable. The quantum physics of materials, the band theory, and semiconductor science that had produced the transistor was not standing still either. And the direction it was moving would reshape the relationship between quantum physics and everyday life more concretely and more quickly than any quantum computer on any current timeline. The semiconductor story had not stopped in 1947 when Bardeen and Brattain built their point contact transistor on a slab of germanium. It had accelerated. And by the early 21st century, the consequences of that acceleration had created a situation that the founders of the transistor could not have anticipated, and that the engineers building it today find genuinely alarming. Because the physics that made the transistor possible was approaching its own natural limit, and that limit was set by quantum mechanics itself. To understand why, you need to trace what happened to the transistor between 1947 and now. The story is one of almost unbroken miniaturization. Each generation of chips packed more transistors into the same area, switching faster and consuming less power per operation. Gordon Moore's 1965 observation that transistor density doubled roughly every 2 years became an organizing principle for the entire semiconductor industry, a self-fulfilling prophecy that companies and research institutions aligned their roadmaps to meet. For decades, meeting it required extraordinary engineering, but the physics cooperated. Smaller transistors worked better, they switched faster, leaked less current, and could be packed more densely, producing exponential improvements in computational performance at roughly constant cost. But miniaturization has a floor. You cannot make a transistor smaller than an atom, and as transistor dimensions approached the nanometer scale, something uncomfortable began to happen. The quantum effects that had been exploited to make transistors work in the first place started working against the design. Here is the specific problem. A transistor works by controlling the flow of current through a semiconductor channel. In an off-state transistor, there is an energy barrier that prevents electrons from flowing. The barrier is maintained by a voltage applied to a gate electrode. When the gate voltage changes, the barrier drops, electrons flow, and the transistor switches on. The thinner and shorter the channel, the faster and more efficient the switching. So you make the channel thinner. You make the gate oxide, the insulating layer between the gate electrode and the semiconductor, thinner too. Thinner gate oxide means tighter control of the channel, which means the transistor works better. But when the gate oxide becomes just a few nanometers thick, just a few dozen atoms across, quantum tunneling becomes significant. Electrons do not need to overcome the barrier, they tunnel through it. Current leaks through a transistor that is supposed to be switched off. The transistor is still technically functional, but it is no longer properly off. It dissipates power constantly, it generates heat, and because billions of transistors on a chip are all leaking simultaneously, the aggregate effect is substantial. This leakage current became one of the central engineering challenges of advanced semiconductor manufacturing in the 2000s, and it did not go away when engineers developed clever solutions. It just changed character as dimensions continued to shrink. The industry response was ingenious and expensive. Engineers moved from planar transistor designs to three-dimensional structures called FinFETs, where the semiconductor channel rose vertically from the chip surface like a fin, allowing the gate electrode to wrap around 3 sides instead of 1, providing much better electrostatic control of the channel. This worked, and it allowed miniaturization to continue past the point where planar transistors would have failed. But FinFETs were harder to manufacture, required tighter process control, and represented a fundamental redesign of the device architecture that had served the industry for decades. The next step was gate-all-around transistors, where the gate wrapped completely around a thin wire-like semiconductor channel called a nanosheet, giving 4 sides of electrostatic control instead of 3. The first processors built on gate-all-around technology entered production in the early 2020s. The channel widths involved were measured in nanometers. The atomic scale precision required to manufacture them was unprecedented in the history of industrial production. And underneath all of this engineering effort was a deeper reality that the industry was reluctant to state plainly. Each new generation of process technology was harder and more expensive than the last, The cost of building a leading-edge semiconductor fabrication facility had grown from roughly $1 billion in the 90s to over $20 billion by the early 2020s. The number of companies capable of operating at the leading edge had shrunk to essentially three: TSMC in Taiwan, Samsung in South Korea, and Intel in the United States, though Intel had fallen significantly behind the other two and was fighting to close the gap. The geographical concentration of the most advanced semiconductor manufacturing in Taiwan in particular had become a geopolitical concern of the first order because production was essential to the chips in virtually every advanced electronic product in the world, and the geopolitical status of Taiwan was not stable. This was the situation that the broader world became aware of, abruptly and uncomfortably, during the global semiconductor shortage of 2020 and 2021. The shortage had multiple causes. Pandemic-related factory shutdowns disrupted supply chains. Demand for consumer electronics surged as people worked from home. Automotive manufacturers who had cut chip orders early in the pandemic found themselves at the back of a very long queue when demand recovered. The result was production lines idled for lack of microcontrollers worth a few dollars apiece. The economic losses ran into the hundreds of billions of dollars. Automobile production fell by millions of vehicles. The episode made visible to everyone what specialists had known for years, that the physical production of advanced semiconductors was one of the most concentrated, fragile, and strategically critical supply chains in the global economy. The United States government responded with the CHIPS and Science Act, signed into law in August of 2022, committing approximately $52 billion to domestic semiconductor manufacturing research, with the explicit goal of reducing dependence on Asian manufacturing and rebuilding American fabrication capacity that had been largely offshored over the previous 3 decades. Similar legislation followed in Europe and Japan. The era of treating semiconductor manufacturing as a purely commercial matter, subject only to the ordinary logic of comparative advantage and global supply chains, was over. It had become a matter of national security in the most literal sense. The deeper physics question underneath all of this was whether the miniaturization trajectory could continue at all, and if not, what would replace it. Because if transistors could not keep shrinking, then the improvements in computational performance that the entire digital economy had come to depend upon would slow down or stop. Not immediately and not completely, because there were other ways to improve performance besides shrinking individual transistors. You could use multiple processor cores. You could design chips specialized for particular tasks rather than general computation. You could improve memory architecture and reduce the energy cost of moving data. But none of these alternatives replicated the broad, reliable compounding improvements that transistor miniaturization had delivered for 60 years. This is where quantum mechanics appeared in a new and unexpected role, not as a problem to be engineered around, but as a potential solution. The same quantum effects that were causing leakage in classical transistors at small scales, the same tunneling and quantization that complicated the design of sub-5 nanometer devices, were in some context exploitable rather than harmful. And researchers began asking whether entirely new classes of quantum devices, not quantum computers in the full fault-tolerant sense, but devices that operated on quantum principles in more modest ways, might offer capabilities that classical electronics could not match. One example was the development of quantum sensors. The precision with which quantum systems could be manipulated and measured made them extraordinarily sensitive detectors of physical quantities. Atomic clocks, which we discussed earlier, were one instance, but quantum sensing extended far beyond timekeeping. Devices based on nitrogen vacancy centers in diamond, tiny atomic defects whose quantum spin states responded to magnetic fields with remarkable sensitivity, were being developed as sensors for magnetic imaging with nanometer resolution. Applications ranged from mapping the magnetic fields produced by neural activity in the brain, potentially transforming brain imaging, to detecting the minute magnetic signatures of geological formations, with implications for mineral exploration and submarine navigation. Quantum gravimeters, based on the interference of matter waves from laser-cooled atoms, could measure variations in the strength of gravitational fields with sensitivity far exceeding any classical instrument. The applications included detecting underground structures from the surface, monitoring groundwater levels, and providing inertial navigation that did not depend on GPS signals. This last application was militarily significant for obvious reasons. From a navigation system that did not require external signals and could not be jammed or spoofed was highly desirable for submarines, aircraft, and autonomous systems operating in contested environments. From the pattern that was emerging across all of these applications, quantum computing, quantum communication, quantum sensing, and the continued evolution of classical semiconductor technology, was not the simple replacement of one paradigm by another. It was a layering. Classical computing was not going away. It would continue to improve through architectural innovation, if not through continued miniaturization of individual devices. Quantum computing would eventually add capabilities that classical computing could not match for specific classes of problems, but it would not replace general-purpose classical machines for the vast range of tasks that did not require quantum speedup. Quantum sensing would provide measurement precision that classical instruments could not achieve. Quantum communication would enable cryptographic security with guarantees rooted in physics rather than mathematical assumptions. The overall picture was of a computing and communications landscape becoming fundamentally more complex, with different technologies operating in different regimes, sometimes complementing each other and sometimes competing, with the boundaries between them shifting as the engineering progressed. And sitting underneath all of it, governing the behavior of every device in every regime, were the quantum mechanical principles that Planck and Einstein and Bohr and Heisenberg and Schrödinger had worked out in the first 3 decades of the 20th century. What none of them could have foreseen was how completely those principles would eventually determine the limits of what was technologically possible. The ultraviolet catastrophe that started the whole story was a failure of classical physics to describe how hot objects radiated energy. The catastrophe of the 2020s was almost its mirror image, a failure of the limits that quantum mechanics imposed on classical devices to be engineered away, pushing the technology toward the quantum regime not as a choice but as a physical necessity. The moment that crystallized this most clearly was not a single experiment or announcement, but a convergence of pressures arriving simultaneously. The leading semiconductor manufacturers were publishing roadmaps that acknowledged, for the first time explicitly, that the path to continued improvement required not just smaller features but fundamentally different device physics. The government programs for quantum technology and for domestic semiconductor manufacturing were simultaneously reaching their first major implementation phases. And the theoretical understanding of what quantum computers would be good for had matured enough that the specific problems worth targeting could be named precisely. The convergence had the character of an ending and a beginning at the same time. The classical era of computing, the era that had begun with vacuum tubes and continued through transistors and integrated circuits to the processors in today's devices, was approaching a set of physical boundaries that it could not cross. And the quantum era, which had been predicted for decades and promised for almost as long, was finally close enough that the engineering challenges stood in sharper relief than the theoretical possibilities. What remained was not the question of whether quantum technology would transform the physical world. It was the question of when and at what cost and who would control it when it arrived. The convergence arrived not as a single announcement, but as a series of results, each one meaningful on its own, that together shifted the ground under the entire field. And to understand what those results meant, you have to go back to something established very early in this story, something that has been running as an undercurrent through everything since. The central promise of quantum mechanics was never just that it would give correct predictions. It was that it would eventually explain from first principles why the physical world works the way it does, why matter is stable, why elements have the properties they have, why some materials conduct electricity and others do not, why chemical bonds form and break at the energies they do. The theory had delivered on all of those promises at the level of individual atoms and small molecules. The question was whether it could deliver on them at the scale of the complex systems that actually matter for medicine, energy, and materials science. That question had a specific bottleneck. From simulating the quantum behavior of electrons in molecules and materials on classical computers was, as Feynman had observed in 1981, fundamentally constrained by the exponential growth of quantum states with system size. From a molecule with 30 electrons existed in a superposition of an astronomically large number of electronic configurations, and tracking all of them simultaneously required computational resources that grew exponentially with the number of electrons involved. For small molecules, this was manageable. For molecules of biological or industrial relevance, it was not. Chemists and materials scientists had developed a range of approximation methods that made the calculations tractable, density functional theory being the most widely used, but these approximations introduced errors that were sometimes acceptable and sometimes catastrophic, depending on the system and the property being calculated. The promise of quantum computing for chemistry and materials science was that it would make those calculations exact rather than approximate, at least in principle. A quantum computer with enough fault-tolerant logical qubits could simulate the full quantum state of a molecule without approximation, tracking the correlations between electrons that classical approximation methods systematically missed. The difficulty was that the molecule sizes relevant to drug discovery, catalysis, and battery chemistry required enough logical qubits that building them was far beyond the near-term engineering horizon. But something interesting happened on the way to fault tolerance. Researchers began finding that even the noisy, error-prone quantum hardware of the early 2020s could provide useful information about chemical systems, not by running full fault-tolerant algorithms, but by using hybrid approaches that split the computation between quantum and classical processors. The quantum processor handled the parts of the calculation that were genuinely hard for classical computers, the strongly correlated electron behavior at the heart of a molecule, while classical processors handled the rest. These hybrid algorithms, sometimes called variational quantum eigensolvers, were noisy and limited, but they pointed toward a capability that classical computing alone could not match. The first demonstrations on actual quantum hardware were modest in scale. Calculating the ground state energy of hydrogen, of lithium hydride, of small organic molecules, nothing that mattered to a pharmaceutical company or a materials manufacturer. But the trajectory of the demonstrations tracked the improvement of the hardware, and as hardware improved through the early to mid-2020s, the size of the chemical systems that could be meaningfully addressed by quantum processors began to grow. Not fast enough yet to be practically competitive with the best classical approximation methods for most systems, but fast enough that the crossover point, the point at which quantum simulation would offer a genuine advantage for commercially relevant molecules, began to appear on roadmaps as something other than indefinitely distant. IBM's quantum roadmap, updated regularly and publicly, projected that systems with thousands of logical qubits would be achievable by the late 2020s. If those projections were met, they would place certain chemical simulation problems within reach of quantum advantage. The projections were not guarantees, they were targets, and the history of the field was full of targets that had slipped. But the methodology behind the roadmap had become more rigorous as the hardware had become more sophisticated. The targets were grounded in demonstrated error rates and in theoretical analyses of how error rates needed to improve to achieve fault tolerance, not in aspirational extrapolation. The drug discovery application was the one that attracted the most attention outside the physics community, for obvious reasons. The development of a new drug typically took more than a decade and cost in the range of $2 billion, with the majority of that cost attributable to failures late in the development process, compounds that worked in computational models and in laboratory tests but failed in clinical trials. A significant fraction of those failures were attributable to the limitations of classical computational chemistry. A drug molecule that was incorrectly modeled in its interaction with a target protein or whose metabolic behavior in the body was imprecisely predicted could pass early screening and fail only when tested in humans at enormous cost. The prospect of quantum simulation removing or reducing that uncertainty was enough to attract serious investment from pharmaceutical companies. Several major drug developers entered partnerships with quantum computing companies in the early 2020s, agreeing to test quantum algorithms on problem sets drawn from real drug discovery pipelines. The results of these collaborations were cautious and honest by the standards of the field. From quantum advantage was not yet demonstrated for the problem sizes relevant to actual drug development. But the partnerships established the institutional relationships and the technical understanding that would be needed when the hardware reached the required capability. The materials science application was in some ways even broader. The design of better batteries for electric vehicles and grid storage, better catalysts for the production of green hydrogen, better superconductors for power transmission, and better photovoltaic materials for solar energy conversion all required understanding electron behavior in complex materials at a level of precision that classical computational methods could not reliably provide. Each of these problems had enormous economic and environmental stakes. The transition to clean energy systems depended in part on developing materials with properties that could not be achieved by incremental optimization of existing materials, but required genuinely new compositions and structures, identified through accurate quantum mechanical simulation. The nitrogen fixation problem was a particularly clear example. Nitrogen fixation, the process of converting atmospheric nitrogen into compounds usable by living organisms, is essential to all life. In agriculture, it is accomplished industrially through the Haber-Bosch process, which converts nitrogen and hydrogen into ammonia using an iron catalyst at high temperature and pressure. The Haber-Bosch process is responsible for producing roughly half the nitrogen in the proteins in the bodies of every person alive today. It is also extraordinarily energy-intensive, consuming somewhere between 1 and 2% of global energy production annually and releasing significant quantities of carbon dioxide as a byproduct. In nature, nitrogen fixation is performed at ambient temperature and pressure by certain bacteria using an enzyme called nitrogenase that contains a complex metal cluster at its active site. The chemistry happening at that metal cluster is quantum mechanical and not fully understood despite decades of research. Classical computational methods have been unable to accurately simulate the electronic structure of the nitrogenase active site because the correlations between electrons in that cluster are too strong for the standard approximations to handle. A quantum computer capable of simulating that system accurately might reveal why nitrogenase works so efficiently, and that understanding might point toward the design of artificial catalysts that could replicate the reaction under mild conditions. The energy savings, if such a catalyst could be developed and industrialized, would be enormous, and the reduction in carbon emissions would be significant. This was the kind of application that placed quantum computing in a different frame from the cryptography threat. The cryptography application was essentially adversarial. Quantum computers as a threat to existing security infrastructure, requiring defensive countermeasures and policy responses. The chemistry and materials application was constructive. Quantum computers as tools for solving problems that classical computers could not solve, enabling the development of medicines and materials and energy technologies that would not exist without them. Both were real, both were significant. And understanding that they were different applications on different timelines with different beneficiaries and different risks was important for anyone trying to think clearly about what quantum technology actually meant. One thing that had become clear through the accumulated experimental work of the 2000s and 2010s was that several of the secondary quantum technologies, those not requiring fault-tolerant large-scale quantum computation, were already mature enough for deployment. Quantum key distribution, the use of entangled or single photons to generate cryptographic keys whose security was guaranteed by the laws of physics rather than mathematical hardness, had moved from laboratory demonstration to real-world deployment. Commercial systems were operating on metropolitan fiber networks in several countries. The Chinese satellite quantum communication demonstrations had been followed by the development of ground-based quantum networks in several Chinese cities. In Europe, the EuroQCI initiative aimed to build a quantum communication infrastructure spanning the continent. The security guarantee offered by quantum key distribution was mathematically provable, which was genuinely remarkable. If an eavesdropper attempted to intercept the quantum key, The act of interception would disturb the quantum states of the photons being transmitted, introducing detectable errors in the key. The sender and receiver could check for those errors and, if they found them, discard the key and try again. A key that was successfully established without detected errors was guaranteed by quantum mechanics to be secret. Not probably secret, not computationally secure against foreseeable attacks, but physically guaranteed secret, as long as the quantum channel itself was trusted. The limitation was practical. Quantum signals could not be amplified the way classical signals could, because amplification required measurement and measurement disturbed quantum states. This meant quantum key distribution over fiber was limited by the absorption of the fiber, reaching perhaps a few hundred kilometers before the signal became too weak to use reliably. Extending beyond that required either satellite links, as China had demonstrated, or quantum repeaters, devices that could extend the range of quantum signals using entanglement swapping without measuring the quantum state. Quantum repeaters were technically much harder than quantum key distribution and remained largely in the research phase through the mid-2020s. Building a truly global quantum communication network required solving the repeater problem, and the repeater problem required either better hardware than currently existed or a more clever approach than had yet been demonstrated. Quantum sensing, meanwhile, was advancing on multiple fronts with less controversy and more near-term impact than either quantum computing or quantum communication. The precision of quantum sensors was already finding applications in medical imaging, geology, navigation, and fundamental physics research. Compact atomic clocks based on laser-cooled atoms were being developed for applications where the size and power requirements of full cesium fountain clocks were prohibitive. Quantum gravimeters were being tested for underground imaging and navigation. And the most precise measurements in physics, the ones that probed for deviations from the standard model that might point toward new physics beyond what was currently understood, were being made with quantum systems that exploited entanglement and superposition to push sensitivity below what classical measurement could achieve. The loophole-free Bell tests mentioned earlier were themselves an example of quantum sensing at the frontier of physics. The 2015 experiment by the group at Delft University of Technology, led by Ronald Hansen, used entangled electron spins in diamond nitrogen vacancy centers separated by about 1 1/3 kilometers to perform a Bell test that simultaneously closed all major loopholes. The locality loophole was closed by ensuring the measurement settings were chosen, and the results were recorded before any signal traveling at the speed of light could have connected the two measurement sites. The detection loophole was closed by achieving high enough measurement efficiency that the results could not be explained by selective detection of a biased subset of the entangled pairs. The result was unambiguous. Bell's inequality was violated by more than 15 standard deviations, and the result was published in the journal Nature in October of 2015. This experiment closed a chapter that had been open since Einstein raised the EPR objection in 1935. 80 years of philosophical and experimental argument about whether quantum mechanics was complete, whether local hidden variables could explain the correlations between entangled particles, whether spooky action at a distance was a feature of nature or an artifact of an incomplete theory, all of it resolved in a single clean experimental result. Local hidden variables were ruled out. The correlations were real. The universe was non-local in exactly the way that quantum mechanics had always said it was. The significance of that closure was not primarily practical. It did not produce a new technology or enable a new calculation. What it did was complete the theoretical picture in a way that mattered for anyone thinking carefully about the foundations of physics. Because if local hidden variables were definitively ruled out, then the interpretive questions about quantum mechanics, which interpretation correctly described what was actually happening in the world, became correspondingly sharper. Copenhagen, many worlds, pilot wave theory, and their relatives were not equivalent in their philosophical commitments. They differed on questions about the nature of reality, the role of observers, the meaning of probability, and the existence of branches or hidden variables or instantaneous non-local connections. And those differences, while not currently producing different experimental predictions, were relevant to the development of new theoretical frameworks that might eventually go beyond standard quantum mechanics. Quantum mechanics, as currently formulated, was not the final theory of physics. Every physicist understood this, because quantum mechanics was incompatible with general relativity in a way that had never been fully resolved. The two most successful theories in the history of physics, each correct in its own domain to extraordinary precision, made contradictory assumptions about the nature of spacetime and the nature of matter. General relativity treated spacetime as a smooth continuous manifold that was dynamically shaped by the distribution of mass and energy. Quantum mechanics treated fields and particles as discrete and probabilistic, and its standard formulation did not incorporate the dynamic geometry of general relativity at all. Combining them required a theory of quantum gravity, and despite decades of effort, no such theory had been established. String theory was the most developed candidate, but after decades of mathematical elaboration, it had produced no unique testable prediction. Loop quantum gravity was another approach, based on a direct quantization of the geometric degrees of freedom of general relativity, but it also had not produced a clean experimental signature. The holographic principle and the related idea of the ADS-CFT correspondence developed by Juan Maldacena in 1997 suggested that quantum gravity in a space with certain geometry was equivalent to a quantum field theory without gravity, living on its boundary, a deep and surprising connection that had been enormously productive as a theoretical tool but had not yet led to experimental tests. What had emerged from this theoretical work was a growing sense that information, quantum information specifically, was somehow fundamental to the structure of spacetime itself. The entanglement structure of a quantum state seemed to be related to the geometric structure of spacetime in ways that were not yet fully understood, but were increasingly hard to dismiss as coincidence. The idea sometimes stated as entanglement is what holds spacetime together was speculative, but it was speculative in a direction that some of the most careful theoretical physicists took seriously. The very thing that Einstein had called spooky and found unacceptable was appearing in the deepest attempt to understand the quantum structure of spacetime. His greatest objection to quantum mechanics might turn out to be the key to unifying it with his own greatest achievement. The connection between entanglement and spacetime geometry was not merely a poetic suggestion. It had mathematical substance, and it emerged from an unexpected direction. In 1997, Juan Maldacena at Harvard published a paper proposing that a theory of quantum gravity in a particular kind of curved spacetime was exactly equivalent to a quantum field theory without gravity living on the boundary of that space. The two descriptions, seemingly utterly different in their content, gave identical answers to every physical question that could be posed to either of them. This was the ADS-CFT correspondence, and it was one of the deepest results in theoretical physics in decades. The implications took years to unfold. One that became particularly striking was a result published in 2006 by Shinsei Ryu and Tadashi Takayanagi, who showed that the entanglement entropy of a region in the boundary quantum field theory was proportional to the area of a minimal surface in the bulk spacetime. Entanglement, a quantum information property of the boundary theory, was directly encoding geometric structure in the higher dimensional spacetime. The amount of entanglement between different regions of the boundary determined the shape of the space connecting them. This was not an analogy. It was a mathematical identity, and it raised a question that had no immediate answer but that redirected a significant amount of theoretical attention. If entanglement entropy was proportional to area in the bulk spacetime, and if the bulk spacetime was what we ordinarily think of as physical space, then could it be that spacetime itself, the fabric of the universe, was in some deep sense woven from quantum entanglement? That the reason we experience a connected, continuous space is that the quantum states of the fundamental degrees of freedom are extensively entangled, and that spacetime geometry was an emergent consequence of that entanglement structure? Mark van Ramsdonk at the University of British Columbia pushed this idea into a 2010 paper that became widely discussed. He considered what would happen to the geometry of the bulk spacetime if you gradually reduced the entanglement between two halves of the boundary quantum system. From. The answer from the Ryu-Takayanagi formula was that the two halves of the bulk spacetime would become progressively less connected, pinching off until the two regions were completely disconnected. Remove all the entanglement, and the spacetime tears apart. From. Restore the entanglement, and the spacetime knits back together. The connectivity of spacetime, the fact that here and there are part of the same continuous space, appeared to depend on quantum entanglement between the degrees of freedom that described them. From. Einstein had spent the last decades of his life trying to unify gravity with the rest of physics. He had tried to absorb quantum mechanics into a classical field theory framework which did not work. From. He had tried to unify electromagnetism and gravity in a single geometric theory, which also did not produce a satisfactory result. And the thing he had most firmly rejected, the spooky non-local correlations of entanglement, was now appearing as a candidate for the very mechanism that held spacetime together. From. The thing he found most unacceptable about quantum mechanics might be the key to completing his own program of geometrizing physics. This did not mean the problem was solved. Quantum gravity remained unsolved in the sense that no complete, consistent theory had been established and experimentally tested. From. The ADS-CFT correspondence was a powerful tool, but the spacetimes it described were not the spacetime we actually live in. Our universe had a positive cosmological constant and was expanding, quite different from the negatively curved anti-de Sitter space of the correspondence. From. Extending the insights from ADS-CFT to cosmologically realistic spacetimes was an active research problem without a settled answer. But the direction of travel was significant. The deepest questions in fundamental physics were increasingly being framed in the language of quantum information. From. Entanglement entropy, quantum error correction, tensor networks, computational complexity. These were not peripheral tools borrowed from quantum computing for convenience. They were appearing as the natural mathematical language for describing what spacetime was and how it worked at the quantum level. From. One specific example made this connection particularly vivid. Ahmed Almheiri, Shi Dong, and Daniel Harlow published a paper in 2015 arguing that the way information was stored in the bulk spacetime of the ADS-CFT correspondence had the mathematical structure of a quantum error-correcting code. From. The same formalism that had been developed to protect quantum information from errors in quantum computers was describing how information was organized in a theory of quantum gravity. From. A logical operator acting on a bulk quantum field could be represented by multiple different boundary operators, just as a logical quantum operation on a fault-tolerant quantum computer could be performed by operations on different subsets of the physical qubits that encoded it. From. The redundancy and protection were the same kind of structure in both cases. From. John Preskill, who had coined the term quantum supremacy and had been one of the central figures in developing quantum error correction in the 90s, described this connection as one of the most surprising and beautiful he had encountered in his career. From. The abstract mathematical machinery built to protect quantum computations was illuminating the structure of quantum gravity. The engineers and the cosmologists were, without having planned it, working on the same problem. This fed back into the question of interpretation in a new way. From. For most of the history of quantum mechanics, the various interpretations had been treated as equivalent in their predictions and therefore equally acceptable, a matter of philosophical preference rather than physical fact. From. Copenhagen, many worlds, pilot wave theory, each made the same experimental predictions and therefore each was as good as any other for practical purposes. From. But if spacetime itself emerged from entanglement structure, then interpretations that treated quantum states as merely epistemic, as representing knowledge rather than physical reality, faced a new kind of pressure. From. If quantum states were just probability assignments reflecting an observer's knowledge, then the entanglement that was supposed to be generating spacetime was also just epistemic, which would make spacetime itself epistemic, which was hard to make sense of. From. The interpretive questions, long treated as merely philosophical, were acquiring physical stakes. The many worlds interpretation had a natural advantage in this context. From. If quantum states were physically real and never collapsed, if all branches of the wave function were equally real, then entanglement was a real physical relation between real physical degrees of freedom, and the idea that spacetime geometry was encoded in entanglement structure was straightforwardly coherent. From many worlds was not the only interpretation compatible with the emerging picture, but it sat most comfortably with it, and its standing in the physics community had been rising accordingly. Alongside these theoretical developments, experimental physics was pushing quantum mechanics into regimes that had never been accessible before. For most of its history, quantum mechanics had been tested primarily on single particles or small collections of particles in carefully controlled laboratory conditions. The quantum behavior of larger objects, everyday scale objects, had been assumed rather than observed on the grounds that decoherence, the process by which quantum systems lose their quantum character through interaction with the environment, acted so quickly at macroscopic scales that quantum effects were unobservable in practice. But researchers had been steadily pushing the boundary of how large a quantum superposition they could maintain. Experiments had demonstrated interference effects with molecules containing hundreds of atoms, then thousands. Mechanical oscillators, tiny vibrating cantilevers or drumheads, had been cooled to their quantum ground state and placed in superpositions of different vibrational states. The largest objects placed in spatial superpositions remained microscopic by everyday standards, but each new demonstration pushed the question further. Was there a scale at which quantum mechanics simply stopped applying? Was there some physical mechanism, perhaps related to gravity, that caused wave function collapse at macroscopic scales? Or did quantum mechanics continue to hold at all scales, with the appearance of classical behavior arising purely from decoherence and the practical impossibility of maintaining quantum coherence for large objects? This was the measurement problem in a new form. Not the philosophical question of what wave function collapse meant, but the physical question of whether it was a real process governed by dynamics beyond the Schrödinger equation, or whether it was an effective description of decoherence. Several theoretical physicists had proposed that gravity caused wave function collapse, that the superposition of two macroscopically different mass distributions was unstable in a way that had nothing to do with environmental decoherence, but was a genuine gravitational effect. Roger Penrose had advocated this position for decades, estimating that a superposition of two states differing in gravitational self-energy by an amount equal to Planck's constant divided by a characteristic time would collapse spontaneously on a timescale set by that ratio. Testing this prediction required maintaining superpositions of objects that gravitational effects were significant, while isolating them from environmental decoherence well enough to distinguish gravitational collapse from ordinary decoherence. That was extraordinarily hard experimentally, but experiments aimed at probing the Penrose mechanism were being designed and in some cases conducted by the mid-2020s. The results so far were inconclusive, not because they had tested and failed to find the effect, but because the experiments were not yet sensitive enough to reach the regime where the effect would be expected to appear. The possibility that gravity-modified quantum mechanics at some scale had a significance that went beyond the measurement problem. If it were true, it would mean that quantum mechanics was not the final theory. It would mean there was dynamics beyond the Schrödinger equation, dynamics that became relevant at the intersection of quantum and gravitational physics. That would be a major discovery, comparable in its implications to the discovery of quantum mechanics itself. And it would answer at least partially the question of why the quantum world of superpositions and entanglement did not seem to persist into the classical world of definite outcomes and macroscopic objects. Now here is the surprising detail that changed the broader interpretation of everything discussed tonight, and it concerns something that appears modest by comparison with quantum gravity and the foundations of space-time, but whose implications cut to the core of how quantum mechanics relates to biology and life itself. For most of the 20th century, quantum mechanics was understood to be real in direct sense. Chemical bonds were quantum mechanical. Enzyme catalysis depended on quantum mechanical electron transfer. Mutations arose from quantum mechanical processes in DNA. All of that was understood, in the sense that all chemistry was quantum mechanical. The interesting quantum phenomena, superposition, entanglement, coherence, were assumed to be irrelevant in biological systems at physiological temperatures. The thermal noise in a warm, wet cell was simply too large to maintain quantum coherence for any useful length of time. Biological evolution would not have found any way to exploit quantum coherence, because coherence would decay before it could do anything useful. From that assumption began to crack in the 2000s, and it cracked in a remarkable place: photosynthesis. In 2007, Gregory Engel and colleagues at the University of California, Berkeley, published measurements of energy transfer in a photosynthetic protein complex from green sulfur bacteria called the Fenner-Matthews-Olsen complex. This protein captures light energy and transfers it to a reaction center where it is converted into chemical energy. What Engel's team found was evidence of quantum coherence in that energy transfer process, oscillating signals that persisted for hundreds of femtoseconds under near physiological conditions, far longer than anyone had expected quantum coherence to survive in a warm biological molecule. The interpretation of these results was immediately controversial. The oscillations were real, but what they meant was not immediately clear. Were they evidence of quantum coherence in the biological sense of superposition of energy states, quantum interference between different transfer pathways? Or were they vibrational oscillations in the molecular scaffold, classical in character despite looking like quantum coherence in the measurements? The debate was technically complex and not resolved quickly. Subsequent theoretical and experimental work suggested that the situation was subtle, that both quantum and classical oscillations were present, and that separating their contributions required great care. But the debate itself was consequential. It opened a field called quantum biology and prompted serious scientific investigation of whether quantum mechanical phenomena like coherence, tunneling, and entanglement played functional roles in biological processes that had evolved to exploit them. Enzyme catalysis, which had long been known to involve proton and electron tunneling, was re-examined with greater attention to whether the tunneling was a passive quantum mechanical background effect, or something that enzymes had been shaped by evolution to enhance. The magnetic navigation of migratory birds, which was sensitive to very small changes in magnetic field orientation, was proposed to depend on quantum entanglement between electron spins in cryptochrome proteins in the bird's eyes, with the entangled spin pairs acting as a biochemical compass. This radical proposal, the radical pair mechanism, was taken seriously enough to generate substantial experimental investigation. The significance of quantum biology, if the functional roles of quantum coherence and entanglement in biological systems were confirmed, would be difficult to overstate. It would mean that evolution had discovered how to exploit quantum mechanical phenomena in warm, wet, noisy environments where those effects were supposedly impossible. It would mean that the tools of quantum information, understanding entanglement and coherence as functional resources, were not just relevant to silicon chips cooled to near absolute zero. They were relevant to understanding how life worked. And it would mean that the boundary between the quantum world and the biological world was not where everyone had assumed it was. The question was still open as of the mid-2020s. The evidence for functional quantum effects in photosynthesis had become more nuanced rather than cleaner with further investigation. The evidence for the radical pair mechanism in bird navigation had become stronger. The evidence for quantum tunneling in enzyme catalysis was robust. Whether these effects were evolutionary adaptations specifically tuned by natural selection to exploit quantum mechanics, or whether they were simply background quantum effects present in all chemistry, but especially visible in certain biological systems, remained a matter of active research and genuine uncertainty. But the frame around the question had shifted permanently. The assumption that quantum mechanics was irrelevant to biology above the level of basic chemistry had been displaced by curiosity and investigation. And that shift in frame was itself a consequence of the larger shift that quantum mechanics had been driving for a century. The progressive expansion of the domain in which quantum mechanical principles were understood to be operative. From black-body radiation to the structure of atoms, from atomic spectra to chemical bonding, from semiconductor devices to quantum computers, from the foundations of space-time to the molecular machinery of living cells. The reach of the theory kept expanding, and each expansion revealed not a simpler picture but a richer and more deeply connected one. Planck had introduced the quantum in 1900 as a mathematical trick to fix a calculation that would not work otherwise. He thought it was a temporary measure, a placeholder, until someone found the proper classical explanation. That explanation never came because there was none to find. What came instead, over the following century and a quarter, was the progressive revelation that the quantum was not a patch on physics. It was the foundation, and the world that rested on that foundation was stranger, more precisely ordered, more deeply interconnected, and more full of possibility than the tidy, nearly finished physics of the 1890s had imagined. The questions that remain open, and there are many, are not small ones. The interpretation of quantum mechanics, the nature of wave function collapse, the relationship between quantum mechanics and general relativity, the role of quantum effects in biological systems. These are not loose ends left by a theory that has otherwise finished its work. They are the frontier of a theory that has never stopped expanding, never settled into comfortable completeness, never stopped producing results that require the revision of assumptions that seemed safe. And that, in the end, is the most honest answer to the question that started this story. Not a question about particles or waves or equations, but about what reality actually is when nobody is looking at it. The honest answer is that we do not fully know. The theory works with extraordinary precision. The predictions are confirmed to decimal places that would have seemed impossible in 1900. The applications are woven into the infrastructure of everything we build and use and rely upon. And yet the nature of what the theory is describing, what is actually happening in the universe when electrons are in superpositions and entangled particles are separated by vast distances and measurements are made, remains genuinely open, genuinely debated, genuinely unresolved. That combination, perfect practical utility alongside deep interpretive uncertainty, is not a failure. It is the actual condition of knowledge at the frontier. And there is something quietly remarkable about the fact that the theory most deeply embedded in the technology of daily life, the theory running in the transistors and the lasers and the sensors and the clocks that structure modern existence, is also the theory that raises the most fundamental unresolved questions about the nature of reality itself. The practical and the profound are, in this case, the same thing. There is a pattern in the history of quantum mechanics that only becomes visible when you look at the whole arc of it. Every time the theory produced a result that seemed merely abstract, merely philosophical, merely mathematical, the result eventually turned out to be pointing at something real and consequential. Planck's constant was a mathematical trick. It became the organizing quantity of all atomic physics. The photon was an overreach. It became the basis of laser solar cells and fiber optic communication. Entanglement was spooky and unacceptable. It became the foundation of quantum cryptography and quantum computing, and, possibly, the key to understanding what space-time is made of. Wave function collapse was a philosophical puzzle with no experimental bearing. It became a question about whether gravity modifies quantum dynamics, with implications for the unification of the two deepest theories in physics. The pattern is not coincidence. It reflects something about the nature of the theory itself. Quantum mechanics is not a description of our ignorance about the world. It is a description of the world. When it says something strange about reality, reality is strange in that way. The strangeness does not dissolve on closer examination. It deepens. And the parts of it that seem most remote from practical consequence have a history, confirmed repeatedly across a century, of becoming the most consequential parts of all. That should change how you think about what is currently unresolved. The interpretation problem, the measurement problem, the relationship between quantum mechanics and gravity, the role of quantum effects in biology. These are not residual puzzles left over from an otherwise finished theory. They are the active frontier of the deepest investigation into the nature of reality that human beings have ever conducted, and the track record of the field suggests that the resolutions, when they come, will not merely settle philosophical debates. They will open new capabilities and new understanding that cannot currently be anticipated. Consider what could not have been anticipated at each previous transition. In 1900, when Planck introduced the quantum, there was no way to foresee that the same constant would explain atomic stability, chemical bonding, the color of stars, the behavior of semiconductors, and the operation of lasers. From. In 1927, when the Copenhagen interpretation was being assembled from the arguments at Solvay, there was no way to foresee that the wave function formalism would become the mathematical language for understanding quantum error correction and the holographic structure of spacetime. From. In 1964, when Bell published his theorem in a minor journal with essentially no immediate attention, there was no way to foresee that the experimental tests of his inequality would eventually seed an entire industry of quantum technology companies and reshape the cryptographic infrastructure of the. From. Global economy. The history of quantum mechanics is a history of the future arriving unexpectedly from the direction of the most abstract and apparently impractical ideas. That is not a guarantee that current abstract ideas will produce specific practical results. It is something more valuable. From. It is evidence that the connection between understanding and capability, between knowing how the universe works and being able to do new things in it, is deeper and more reliable than any straightforward extrapolation from current technology would suggest. You are lying in the dark in a room full of quantum mechanics. From. The chips in every device around you, designed using band theory and quantum tunneling. The signals passing through the walls, electromagnetic radiation whose quantum nature was settled over a century of argument. From. The biological processes in every cell of your body, chemical reactions driven by electron transfer and quantum tunneling in enzyme-active sites, possibly by quantum coherence in processes that evolution may have tuned over billions of years to exploit. From. The atoms in your bones, forged in stellar cores through nuclear fusion that was made possible by quantum tunneling, allowing protons to combine at temperatures that classical physics said were too low for the reaction to proceed. You are not surrounded by quantum mechanics as by some exotic thing. From. You are composed of it. From. Your existence depends on it at every level, from the nuclear processes that built the atoms of which you are made, to the chemical processes that assemble and maintain the molecules that make you a living thing, to the electromagnetic interactions that let you see and hear and feel, to the semiconductor devices that. From. Let you navigate and communicate and store memory. Every layer of the physical story of your existence is a quantum mechanical story, and the part of that story that remains unfinished is the part that might matter most, not the engineering. From. The engineering is progressing, steadily if not always as fast as the press releases suggest. What remains unfinished is the understanding, what the wave function is, what measurement is, whether the universe branches into many worlds or collapses to one. From. Whether spacetime is woven from entanglement or entanglement emerges from spacetime, whether the boundary between quantum and classical is a physical transition governed by new dynamics or an illusion created by decoherence. From. Whether living systems have learned to exploit quantum coherence in ways we have not yet understood, these questions are not going to be answered tonight. They may not be answered in a decade. Some of them may require experimental capabilities that do not yet exist, or theoretical insights that no one has had yet. From. But they are being worked on right now by physicists who carry with them the full weight of the century of argument and discovery that this story has traced. They know where the bodies are buried. They know which approaches have been tried and failed. From. They know which apparent paradoxes turned out to be resolvable and which remained intractable. And they are asking the next questions with tools, both experimental and mathematical, that are more powerful than anything available to any previous generation. From. There is something Niels Bohr said late in his life that has stayed in the physics community, passed from teacher to student, because it captures something true about the experience of working at the frontier of quantum physics. He said that if you are not shocked by quantum mechanics, you have not understood it. From. He was not being dramatic, he was being precise. The theory makes claims about the nature of reality that are genuinely shocking when you take them seriously. Not shocking in the way that a surprising plot twist is shocking, where the surprise resolves into a satisfying new picture. From. Shocking in the way that a deep disorientation is shocking, where the more clearly you see the situation, the more clearly you see that your ordinary categories do not apply. That shock does not diminish with familiarity. Physicists who have worked with quantum mechanics for decades still find it strange. From. The strangeness does not become comfortable, it becomes companionable. You learn to work alongside it, to use it precisely without pretending that you have resolved the mystery at its center, and there is something honest and maybe even valuable in that posture. The universe does not owe us an intuitive picture. It does not have to make sense in terms of the experience of creatures evolved to navigate a macroscopic world of medium-sized objects moving at medium speeds. It just has to be consistent, and it is, with a precision and a robustness that has survived every challenge thrown at it for over 100 years. The story of quantum mechanics is, in the end, a story about the limits of intuition and the power of mathematics to reach beyond those limits. Every person involved in building the theory had to learn to trust the formalism over the picture. To follow the equations into territory where no ordinary image could go and accept what they found there. That required a kind of intellectual courage that is easy to underestimate. These were not people who had grown up expecting the world to be strange in these particular ways. They had to become comfortable with strangeness that had no precedent, guided only by the requirement that the theory match experiment, and it did, every time, to degrees of precision that remain astonishing. So here, at the end of a long night of thinking about small things that turn out to be enormously consequential, is what you can carry into sleep. The universe is being held together right now by quantum mechanical rules that took the smartest people in the history of our species 100 years to begin to understand, and that we still do not understand completely. The electrons in your neurons are doing what quantum mechanics says electrons do. The photons carrying your last visual impressions before you closed your eyes were doing what quantum mechanics says photons do. Everything is working as it is supposed to work, according to laws so deep and so strange that every generation of physicists rediscovers the strangeness and is surprised by it again. That is a good thing to fall asleep to, the knowledge that the world is far stranger and far more precisely ordered than it appears, and that the strangeness and the precision are the same thing. If this kind of slow, careful journey into difficult ideas is something you want more of, subscribing is the simplest way to make sure the next one finds you. New documentaries go up regularly, and there will always be more strange and consequential things to think about slowly in the dark.